morning, all. On behalf of IEEE ComSoc Bangalore Chapter and IEEE Kharagpur Section, I extend a warm welcome to all the participants who have joined us for a workshop on 6G requirement and use cases. Myself, Changappa, along with my colleagues Bidnaraj and Debraj from IIT Kharagpur, would be hosting this workshop and would be with you for the rest of the workshop. So, without much further ado, I would like to invite our chair, Dr. Aloknath De, to set the opening remarks and also formally inaugurate the workshop. Dr. Alok, over to you.
Thank you. Thank you very much. It's a pleasure. And, as you know, from IEEE Bangalore sections, we have been doing many workshops, many programs for students community. And I will not go into those details today. But I really want to appreciate all of you coming and joining. It is a very difficult time. I hope you all are safe and taking care and families are well. It is an important topic on one hand, and we wanted to kickstart this 6G discussion. But at the same time, I'm very cognizant of the fact that, we are going through very difficult time. So on one hand, we have to take care of ourselves, but definitely we need to be mentally strong to set strong footing for India, for newer technologies. So keeping this in mind, as I said, I joined Samsung in 2011, and my first assignment has been on 5G research on MAC layer and bit of top and bottom around that. And since then, it has been 10 years. And Professor Devarati was also part of the team then. Now she's in Kharagpur. We did a lot of good work in the beginning, but there was no standard. Standards came much later. It is in fact 2015-16 timeframe it got started. So first 5-6 years goes into a big research, finding it out what will work. And then eventually you start to build systems, you test, you take it to standards community. And today we are having this deployment worldwide. 2019 March timeframe, we launched in Korea formally. 18 end, we have done a kind of B2B trial, and B2C deployment, we did it in 2019 March timeframe, and this has been 2 years. Obviously, in Korea, it has grown significantly, 10 million plus subscribers that we have seen a couple of months back. But globally, many operators have deployed, and even in India recently, we have talked about the trial. This is opening. Government has approved. Spectrum auctions will happen after that. So on one hand, we are going through the fruit part of it, the last mile part of it, of all the 5G work that we have done. And so it takes 10 years to get to that point. So we from IEEE ComSoc Bangalore, we've been doing many earlier conversations on 5G, on the research, on the technology front. But this year we said we will focus more on the deployment, the challenges, the spectrum, the last mile aspect of it. And I'm very glad to say that with our strong execom and many members, we have been able to progress very significantly in this front. We have done many workshops and continuing to do that on security, on spectrums and other things. But as we do that, this is again a very important and interesting point that we are kickstarting, at least in India context, this 6G discussions. And today I feel for our society, it's a great opportunity to formally start a 6G discussions. We have been doing a bit of B5G, on intelligent reflecting surface, on blockchain and post-quantum security. But I think this will peg a good starting point for the 6G communication. And I should also say that we are doing a summer school. If any of you are students and are interested, from 10th to 12th June, we have declared this is a global summer school, but anchored by Bangalore ComSoc. It's on B5G and IoT, human-machine communication. The program is defined, and it is on the website of Global IEEE ComSoc. 3rd May onwards, the registrations have started. So if you are interested, please feel free. But please, if you are registering, you are really making the commitment to join. So if it is so, then only you please register. And today I'm again pleased. We work with many different societies. We have done with IEEE Delhi and many other societies within Bangalore sections. And that way I'm very glad to partner for the first time, at least in my memory period, with the IEEE Kharagpur. Although we work with them, I am from IIT Kharagpur, so glad to have Professor Misra and Sen for these discussions. But formally between IEEE ComSoc Bangalore and IEEE Kharagpur on this topic, I mean, definitely we can do quite a lot. So again, I am really thankful for them to agree to participate. And Professor Misra has been instrumental in a lot of IoT work. Debarati Sen, she has been working on the communication, the physical layer. So I'm very glad to have it along with our colleague, Dr. Saptarshi, who will talk about the network part. So with that, I will hand over to the organizing committee. Thank you.
Thank you. Thank you, Dr. Alok. Now I request Dr. Sudeep Mishra, Chair IEEE Kharagpur Section, to share his thoughts around this workshop with our participants. Sir, over to you.
Yeah, so thank you, organizers, for me to share my thoughts on and beyond. As Dr. Day said, I and my research group, we have been working on IoT in IIT Kharagpur. Not only IoT but also we have a very strong focus in the GS Channel School of Telecommunications and the Department of Electronics on cellular communication. And there are quite a few researchers. Dr. Debarati Sen is one of them, and there are a few other researchers who are working on this domain. And they are working on the futuristic aspects of cellular communication, 5G and beyond, 6G and more. So we, I, Dr. Sen, and many others who are present over here today, I see many names. We are all part of the IEEE Kharagpur section. And as a section, so at present, actually, I am chairing the section, and there is a strong team. We are a small section, but we have a strong team who has been working on the different aspects of electrical sciences. So we all contribute towards the greater cause of moving forward in the domain of electrical sciences and communications. IEEE Kharagpur section is quite active in our respective domains. So this particular workshop, I'm glad that we could organize, because so far most of these workshops were at least in the Kharagpur section were mostly like standalone and or in the form of conferences. But this kind of workshop, I think this is a good one, which basically inspires us to have joint sessions with other sections and chapters. So I'm very glad that the Kharagpur section is participating with the Bangalore section for this particular important workshop, a futuristic one which is coming, not so distant future. So thank you, Dr. De, for the invitation, and thank you, Bangalore section, also for the invitations, and all the other members in the organizing committee, and also finally, thanks to all the participants for making yourselves available in the early morning on a weekend. Thank you so much.
Thank you. Thank you so much, sir, for sharing your thoughts and brief insights into IEEE Kharagpur section. Now I request my friend Vignaraj to formally introduce our first speaker of the session, Dr. Alok Nath De, so that we can formally kick off the session. Vignaraj, over to you.
Thanks, Chengappa. Welcome everyone for this interesting talk on session on 6G. So, as they say, a well begin is half the job done. So, as a first talk of this session, we have a very renowned personality in the wireless communication world, Dr. Aloknath De. Dr. Aloknath De is a corporate vice president of Samsung Electronics and chief technology officer of Samsung R&D India, Bangalore, where he is responsible for Samsung's IoT data platform and advanced service. Dr. De is considered one of the most influential CXOs of India. He is a recipient of the Alexander Graham Bell Prize in Canada. He has also received IEEE Memorial Awards for distinguished contributions in electronics and communications, IDC Insights Award for Innovation in Telecom, and the Zenov Entrepreneur of the Year Award. He is a senior member of IEEE and a fellow of IETE and Indian National Academy of Engineering. Dr. De promotes science and technology linkage through IP creation, startup collaboration, and innovation solutions. In addition to more than 30 years of industrial and research experience, including Bell, Nortel, Hughes, and with ST Ericsson, where he was country director. He served as a visiting professor with IIT Roorkee and IIT Delhi from 2005 to 2011. Dr. De holds a BTech from IIT Kharagpur and ME from IIC Bangalore and a PhD from McGill University, Montreal. Over to you, Dr. De.
Thank you. Thank you very much. Okay, so my talk title, I said 6G, what will change, because this is the first presentation. And so we will take you through, and as you can see in this pictorial view, there are a lot of interesting applications that could come out of it. So if you move to the next slide. So I'll take 2 slides just to set the stage, a little bit of recapitulations, not knowing 110 people that have joined now. Many of you would be knowing a lot about the 5G, but in case some are not so familiar, let me just very briefly mention that when 5G got started and IMT 2000, effectively 3 things that people talked about. One is the enhanced mobile broadband and throughput, the data, the peak 20 gigabits per second, the edge at 100 megabits per second. People talked about ultra reliability and low latency, right? You can see 1 millisecond latency and very negligible error rate that we must achieve. And third pillar is about massive machine type communications, whereby 10 to the power 6 connections per kilometer square was defined. And at the same time, some devices should be able to live with 10-year battery life. Now, when you set the goal, you achieve some, you may not achieve all. And in the process, you figure it out that you have to do more work. On the right side, you see that not just those 3 main pillars, but if you would like to expand, you get an octagon. And beyond those 3 points, you also get a spectrum efficiency that needs to be improved. And the inner diagram shows what was achieved in the LT and going on to the 5G's thing, whether it is a mobility speed that we need to increase, connection density. And when you have a lot of devices and people, then your area traffic capacity becomes another factor. And we talk about green energy and therefore network energy efficiency. So this spectrum you must have seen quite a lot, and definitely we would have an equivalent 60 definitions. Now, I said 2011, and that is us, we started researching, and as you can see, the standard evolving beyond this is 3GPP standard below that you can see. Release 14, that's the beginning of 5G standardizations. Obviously, LTE advanced was there before. And then you come step by step. First was non-standalone in release 15 was a focus towards the end of its standalone. And then we went into 16. 17 is ongoing, which got delayed due to COVID. It will be 9 months delayed to next March, April timeframe. And that will also be a kind of 5G component, but from release 18 onwards, standard body has decided to call it 5G advanced, beyond 5G, 5G advanced kind of it. And I told you about our journey from Pyeongchang Winter Olympics in 2018 as a trial, not in the same form factor, going into SK Telecom, KT, Sprint, Verizon. Today, there are many operators in Canada, New Zealand. We are, as Samsung, working alongside our own devices. Obviously, the Summer Olympics didn't happen, and hopefully, as it progresses, we should be able to get a bigger picture of the 5G. Moving to the next slide, that talks about 5G we considered as a backhaul. And why I'm saying this is to prepare mind that also for 6G, this will be coming more and more. That it is not just the backhaul, but also it is about penultimate mile or the last mile. Last mile is the fixed wireless access that we talk about. But even on the penultimate mile like this, you have a 5G core and access units. I always jokingly say the street lights are very, very important. More than the lights, probably there would be communication mini tower. So we have to safeguard them the way they get, destroyed at times. I worry that if we serve this as communication nodes, what will happen? We have to have a lot of redundancies. But coming to the point here, LTE small cell, public Wi-Fi, the IoT sensors, the CCTV, the digital signage. I gave a rough pictures with some indicative numbers. And when you combine all of them, they become a gigabit traffic. So today we are talking gigabit traffic, and this is the 5G's penultimate mile. But yes, in the home also, we are talking about fixed wireless access. So I think this is good enough for coming to the point that what we are doing for 5G and how we'll be deploying. Now, next slide will start to give what are the fundamental macro changes. So we always get guided by some macro scenario changes. Now, obviously, that octagon that I showed, definitely they will be a next step. Some cases 10x, some cases 1/10th in latency. That's a natural progression because we get a lot of technologies of AI and IoT and new technology that are coming. They will give you extra edge in the next 10 years. Now we're talking between 21 and 30 kind of windows. But just to keep few points in mind, one is the users experiencing rich media services, right? That's very, very vital because plethora of these services, whether it is data, image, animations, video, all kinds of multimedia, that will be integral part of the communication content. So that's one change that would require quite a lot of things because the 3D, the VR, AR, all these would be part of this. The second change is humans becoming more and more connected, the hyper-connected world. And IoT we are bringing, and 5G already talks about beyond people-to-people communication. People-to-things are already into place. People-to-things in 5G advanced are getting a bit more enriched. But I think 6G will also talk about things-to-things communication. So that is very, very vital to understand that it's not people-to-things, and it's not even people-initiated. It could be thing-initiated. And therefore, there could be a lot of interesting problem statement around this. And the third point is in another way, as we see the COVID time, we have really realized that importance of the cyber world, the digital world. If we are not having this digital world today, we have been very crippled if we are quite dependent only on the physical systems. But now we got the hang of cyber systems. I think a right balance of cyber physical systems, many calls it phygital, physical and digital systems. So we believe the 6G system will be serving as backbone for these infrastructure. So with this macro scenario, let me go into next set of 7 points I'm going to highlight, and we'll take it. I'll not take you through these slides in details. These are indicative slides. This is the first discussion on 6G. So I have no intent to take you through, but some of the subsequent speakers are going to cover some of these aspects, and we have next 5-7 years to talk more about these in details. So on each of these topics, these are picked up from different sources, the pictorial views. I'll give you some maybe 3 points. What's changing? That's my focus. So let me talk about, let's focus on that, and let me see if I could highlight a couple of points there. So first is terahertz communication. In terahertz communication, as I said, rich media services, a lot of holographic videos, and they will require a bandwidth that is currently unavailable in the millimeter wave spectrum. A broader RF spectrum bandwidth will become necessity and can only be found at the sub-terahertz and terahertz bandwidth. Sub-terahertz, this whole range could be 0.1 terahertz to 10 terahertz. That's where people are starting to work. And I, again, want to emphasize there is no 6G standard. Nobody knows what will come. So do not think that this is right, that is wrong. It is in brainstorming sessions the world is going through and exploring which part of it would work. So first thing people are trying to do, and FCC in US has opened that spectrum between 95 gigahertz and 3000 gigahertz for experimental use and even unlicensed applications to encourage some development of new wireless communication technologies. So you will see in a recent ICC that is coming up, a couple of papers that you would see, and terahertz communication, the vision is above 100 gigahertz, because up to 60 gigahertz, a lot of companies and academia have explored in the first round. But can we start to prove that it works 100 gigahertz plus scenario? So this is a first focus that people are putting. The second point I wanted to highlight, that as you go into this terahertz bandwidth, and since there is a necessary, as I said, holographic videos and things like that, those applications, the other aspect that will be coming is indoor and outdoor environments. Now, as you know, most of you would know that the absorption lines for oxygen and water are mostly located in this terahertz bandwidth. And I'm sure Professor Devaruti will talk about that more, but this requires studying some kind of tractable yet accurate terahertz multipath channel models for both indoor and outdoor. And you need this MIMO that already we did it, sophisticated techniques for beamforming, but we have to do even further development for this energy efficiency. And I believe MIMO is now going to be shaping up as some kind of ultra MIMO for an overall system performance. So you might start to hear more. This multiple has been a bit lesser in numbers, 2x2, 4x4, but this is going to be changing, and an ultra MIMO concept should be emerging. And third point on this is, communication links at terahertz frequency will depend on line of sight, but also on focused reflected paths. Not so much on scattering and diffracting, but really focused reflecting paths. And we had a sessions on this intelligent reflecting surface that tune that wireless propagation environment with an array of IRS units, and that could play some critical role in 6G system design. Will WaveDM still be there, the remaining waveform of choice, or some other waveform will come? That needs to be seen. And many of those are seeing into kind of, I don't know, I lost the slide deck. Yeah, many of them would be coming into this, the silicon part, and this silicon would be not just the silicon, but indium phosphide, gallium arsenide, silicon germanium, lot of low power concepts, energy efficiency would also be explored. So I'll stop here on this topic and you could have reference to study further. The second point, next slide, is on the network configurations. And we talk about today much more fixed topological configurations, but I think we'll move towards flexible network deployment that helps to accommodate in terms of data traffic. And 6G must cover the whole universe, right? So any holes that are currently there in population coverage needs to be done. An ad hoc network forming for some critical services. Mesh type network are going to be coming up. So at the end, our goal is high precision, location, and dynamic network configuration. This is one dimension that is very, very vital, and that's quite significant change from today's solutions. The second part I would like to talk in this network configuration is we have seen already, today we have open source. Because these equipments are becoming bigger and monolithic deployment would not work, even though this is not directly contributing, but the whole business model, the engagement, the entrepreneurships, that could change significantly for realizing complex network functions. How can you use open source modules? How can you develop them, conceptualize for core networks, for base stations? And today we already have seen ORAN, Open and Intelligent Radio Access Network, ONAP, the Open Network Automation Platform. That's all today's knowledge, but I think these would be significantly moving up and tuning as 6G system gets into that directions. And I think the open source based intelligence software modules would be starting to come. But as that happens, I think we would also see some system vulnerabilities and attack surfaces that could be coming. So this we need to take care. The third point on this network configuration that I wanted to say is that today, first generation, second generation, we talked about cellular system and we went into cell-less system. 6G, not yet gone, but I think quite a lot would be cell-less systems because it is no more terrestrial network. It would be embracing in a significant way for global wide coverage, non-terrestrial networks. As you can see in the diagram, the ships, the cruisers, the robos, and you have drones, the UAVs, satellites, you will have HAPS, high altitude platform stations. They all would become very part and parcel of the integrated communication systems. And not just individual communications and mobility, but really it would go into group mobility. Group mobility, when people move together, how can you give them a service? So I think this is something that we are looking for the network evolution change. And I'm sure Dr. Saptarshi will talk a bit more on these network dimensions. Moving to next slide is on the IoT and the machine type communications. And you can see from 5G network architecture changing to the 6G. But let me highlight again some key points. What I already mentioned, you may not be even initiating by person, but it can be things initiated and machine type communication, things to things, and all the applications, smart cities, smart manufacturing, other smart entities, the ubiquitous connectivity that will come anytime, anywhere that we talk about. We have achieved to some extent, but I'm sure this would become a very big basis for the 6G, including the things. The second point I wanted to highlight here is these devices, machine type devices, are of various categories, form, size, and low power sensors, sometimes powered by micro batteries. Some energy harvesters would be there. So the fundamental question in my mind is what design enablement has to happen for such low cost, low power receivers? Because many of them has to be awake to get cognizance of what's going around, but also have to be sleeping, because otherwise you will drain out the battery. So the sleep mode definition would go through a big change. It may sound like a small thing, but it is not, because highly efficient sleep modes, when to sleep and when to be awake, is something for ultra low power MTC devices would become very, very important. And then it comes mission critical, dependable MTCs, and all kinds of devices that I talked about, UAV based swarms in groups, not just people in groups, but things in groups. You have seen many times, all these drones in the sky, instead of fireworks, they have started showing, and in fact, even advertisements have started coming up with the drones. So when they are deployed in shop floors, connected logistics, it can be quite interesting job onto its own. So this whole group communications and interactivity among them, among the things, not just among the people, is one vital aspect that will be emerging. The third point I wanted to highlight on this is we are classifying. We have started classifying, and some papers have come into how many classes we will do depending on applications. This machine communication, there is this critical machine type communication, there is massive machine type communication, there would be dependable kind of machine type, and then you might combine dependability with criticality or massiveness or broadband requirement or low latency or high reliability. When you combine all these, you might start to define new classes of types of communications, machine types of communication. And all of them are different. Like, robotic aided surgery would be very different than if you want to do a factory monitoring versus if you go to the precision agriculture. So they would be different. And how many devices you could deploy, how long would be the lifetime is something that would come. So I think you got to hang off the machine type communication, and we have Professor Sudeep here, and he would talk on the IoT synergy part. So I would leave it here and move to the next slide, which is my fourth out of the 7 topics, is augmented intelligence. So this is on the AI part of it. We need to, in 5G systems, we are doing this AI very ad hoc. I mean, there are some machine learning algorithms that they might have been included in vision part and this part and that part, but the true communication part, it is all kind of a posteriori application in 5G. In this layer, can I look into the data and see it? So in network management or certain interfaces, because AI was not a charter in the 5G definitions in a big way. This will change. And as you can see below, in the computing nodes with the simple response, whether it is source compression, channel coding, their joint optimization, or end-to-end analysis for system error performance, these would be all pervasive. We will define AI in each of these layers, and they will start to play and make it intelligent at every layer. This is the change that we are going to be seeing in the 6G. The second point that is vital there is in terms of even the spectrum, not just the system design, but with the help of AI algorithms. Today, we have a lot of underutilization for spectrum sharing with other operators even. You have you're not utilizing certain spectrum, but somebody else would like to use it, but you can't do that. There is no mechanism, and it's all separate contracts and things like that. So I think in future, we could do this, allowing opportunistic use of the underutilized spectrum in a smart way and pay to the others, not free. but you can use the best use of the limited spectrum resource, the dynamic spectrum sharing, and a lot of such thing application of AI in the limited information exchange. We can predict, we can utilize, and this is one area I think it can significantly grow. The third part I wanted to talk in this augmented intelligence segment, that's a must. That also is a kind of new technology in the AI context today, not being deployed, not fully understood, but by 60 time, this would be solid. This has to be solid. That's about explainable AI. From the legal standpoint, because we would be doing a lot of mission critical things and criticals. So therefore, these conventional algorithms to deep learning, and if you put it in all layers, since today we are not putting in communication, it is in the interface, it's more like data management. But when you put inside, then it better be explainable. And that explainable AI, I do a 23 layer CNN, but I can't say what is happening at the 16th layer and what's the value of the 17th layer. But these kinds of concepts, the neural network model pruning that can bring lower complexity, brings more explainability, this has to be expanded. And the concept of XAI, explainable AI, is in my mind is a must, and it will help in the legal ways also if it requires for enabling trust in the future wireless systems. So with that, I move to my fifth item in the next slide, which is kind of linked, if you move to the next slide, of the edge computing. Now this, with so many devices coming, and we have today cloud, today's move is all cloud native, cloud architecture, and we are getting into public-private cloud, the hybrid cloud, 5G, a lot of such partnerships and deployment we can see. And that's great. But I think as we move from 5G to 6G, this edge will start to play a big role. And I gave example, but many of these devices will be thin devices. Some will be having processing power. We'll go through that change also. We don't know whether devices will remain very powerful or they can be thin, but watch to soundbars to VR headsets to augmented reality glasses, many things are coming up. So the question is, what is not possible by human being? Can we deliver some performance superior than that in the 6G communication infrastructure? And how do you leverage these devices, and how do you define what could be done on device, what could be in the edge layer, what could be in the cloud? That's something that would be figured out. And as a corollary, the second aspect I wanted to say is that this smart splitting of computations between hardware, software, and between devices is going to be an important part, and intelligent offloading of certain things from one to the other would be very, very important. So we see that kind of trend. And whenever the algorithm complexity is high, but the processing possibly, if it's big enough, then may have to be split in some sense. So with that, I think the third point I wanted to highlight here is that this explainable AI and the devices and IoT we talked about, and today we talk really Internet of Intelligent Things to some extent, because things itself are becoming intelligent. But how do you make even internet to be intelligent, and intelligent transportation system, powerful fog servers and edge? So not just the cloud and the device, but the cloud fog, which is closer to the cloud, but edge, which is closer to the devices. And how do you mix them up and offload? This is one interesting area, and a broad vision for 6G edge intelligence. I would take time, but this is the direction in which it is going. So that brings me to my sixth point in the next slide, which I wanted to highlight on the security, privacy, and trustworthiness. And this as we make it more modular, more players are building this whole network, this user devices could be hacked. These are things. So two reasons. One is these things, many of them are cheaper devices. They don't implement fully all the security, and possibly they don't have the memory and processes to do it. Many of them will come from startups and new companies. So on one hand, that remains a fact and that brings innovation, but on the other hand, that brings a vulnerability to the overall system. So where do you draw a line? And conventional authentication, authorization, verification is not possible because tons of devices will connect. So how do you do an auto authentications, given that this device belongs to me and some other devices through some account informations and others? People would look into that. But yes, we also talked about quantum key distribution. We had a special session on security and towards the ensuring the long-term security of data. So we figured out the security of quantum key distribution is based on the quantum effects requiring an optical channel, whereas the post-quantum cryptography is actually aims at circumventing some threats that could come from quantum computers. And this is also important to note that these are evolutions that is going to be happening and on the side, and they pose further challenges to this system. So effectively, then the second point is, can you use this blockchains and distributed ledger technology and assume that the trust, this is a zero trust system, and connect them, right? Instead of assuming and connecting only with the trusted parties, assume that zero trust, and how can you bring those informations to connect it? So that's an area that's going to be nurtured more and more. And we have talked a little bit into our workshops other time. Third point I wanted to highlight here is it is not always technical. The challenges in creating a trustworthy 6G, which would be a goal, more than the term of security and privacy, I think we'll hear trust. It spans from technology to regulations to techno-economics to ethics to politics. I think it spans in every places in this hyper-connected world. And then there is this fake content that are coming. What is real? What is fake? So it's a very vast topic. And I'm sure people would like to achieve what they can in this limited time. But I won't be surprised if some of these get moved to the 7G definitions. So I think I wanted to highlight on this security, privacy, trustworthiness, and so many devices getting connected in so many ways, and open source modules and other ways. This is the crux of success for 6G systems. With that, I come to my last slide on this seventh point is on the rich media services. And this I took it from Samsung's 6G vision. We have published this material, the next hyperconnected experience for all. It has many items that I also described so far, particularly on the physical layer and others. But I just picked up this as an example for the applications. So truly immersive XR or high fidelity mobile hologram or the digital replica. These are kind of applications that are anticipated with device form factors, handheld components. So I think applications would grow into interactive tactile internet or fast moving games. They would require all of those factors we talked about, the latency less than 100 microseconds. At least, algorithmically, maybe end-to-end could be less than 1 millisecond deployment. Extremely low jitter. So all those would be required for such applications. So in particular, the point I wanted to highlight in second point is that hologram is the next generation media technology. Many other things are already there. They will grow. But this technology can present gestures, facial expressions by means of holographic display. And all these device companies would also work on the capturing, transmission, 3D rendering, 3D hologram displays. So there's a lot that will happen into those directions. And if you open this white paper, you would find some calculation. Just to pick up one from there, a detailed calculation will establish that hologram display over a mobile device would require at least 0.5 terabits per second, vis-a-vis the typical peak data rate that we get, like 20 gigabits per second in present 5G systems. I earlier said that you can't do it in the 5G. So to do hologram, you need to move to 6G in a big way if you wanted to do. And the third point I wanted to highlight, which is again connecting to the things, the exponential growth on the number of connected machines will require 6G to support like 10 to the power 7 devices per square kilometer. We will expect some ultra dense deployment of industrial IoT devices, connectivity, maybe 3D connectivity concept. The industry 4.0, we are saying that will move to 5.0, which will include a lot of interactivity, AI infused twins, cyber physical systems. These all would be coming, and we have to make sure that things-based services or things included services becomes part of that rich media services. So with that, I kind of highlighted 7 important points. And just to recap, the terahertz communication, the network configurations, the machine type communications, the augmented intelligence, the edge computing, the security, privacy, and trustworthiness, and rich media services. So moving to the next slide, just to say thank you. Thank you for your attention. And I'm also glad to say that, we have been able to, some of us have got together and edited this book, 6G Mobile Wireless Networks. Springer tells us that this is the world's first 6G book. So that's their kind of comment. And we are happy to combine a lot of work from different parts of the globe to bring it. Hopefully this month and or June, it will be physical copies would be out. So with that, I say thank you, and thank you for your rapt attentions. If there is any questions, otherwise we'll move to the next presentation. Thank you very much.
Thank you, Dr. Dey. For the in the benefit of time, the questions we would take it at the last for all the speakers, and participants, you can put your questions in the Q&A block in the interface. So I once again thank you, Dr. Dey, for enlightening us with an extremely and informative talk. You highlighted many aspects and roles of terahertz, IoT, AI, XAI, edge, security, etc., which are very essential for moving forward towards 6G. So on behalf of the organizing committee of IEEE ComSoc Bangalore Chapter, I would like to again thank you, Dr. Dey. So our next talk in line is on 6G cellular network features, scope and challenges. We have Dr. Saptarshi Chaudhary, who is a chief architect from Redishes. He has more than 24 years of extensive working experience broadly in wireless communication domain, in particular 6G, 5G research, 5G system simulations, LTE, LTE algorithm research and design, 2G, 3G, 4G wireless product, that is RAN, EPC, etc. He has filed more than 120 patent applications across multiple countries in the area of RAN network slicing, NOMA, RRM, scheduler, sound, data offload, D2D, CRAN, Li-Fi, with 37 granted US patents and 3 granted European patents. He has authored 15 international peer-reviewed conference and journal papers. He holds IEEE senior member position along with IEEE ComSoc Bangalore Section. I welcome you, Dr. Saptarshi.
Yeah, thank you, Vengaraj. So, Vengaraj, somehow my share button content is.
Yeah, 1 second.
Yeah.
Changappa, if you can. Now, can you try, sir? Yes.
You able to see my
Yeah,
screen?
we are able to.
Okay, let me get into the presentation mode. Okay, so I think Dr. Alok just gave the right context of what the 6G will look like. And it's a journey, actually. We have been part of this journey, at least from the 5G world, we have seen it, 4G world, we have seen it. And part of my close to 25 years now, I have been part of the journey seeing from the 2G days itself, when the first base station got unfolded in India. And we were wondering what this box magic does from the GSM technology. Now, 25 years from there, actually, we have seen the revolution of the communication. That point of time, way back in 94, 95, when the first call we made it, we were so excited to hold a big mobile. It's not a small mobile that point of time. And it was the first network in 1994 where Modi Telstra made a first call in India. The network that has been revolved, actually, we have seen the migration, like how a network makes services, because what a service means, the definitions was okay at that point of time when we talk about voice-based approach, and that was the main services that we were all talking about. From the textbook approach, actually, we were all told when we all passed out and when we started becoming a practitioner of this technology, in our mind, we were all taught with the OSI layers that how OSI layers will do the computer communications. But when we entered to the cellular world, actually, when we made the first call, we were trying to figure it out that what is the relevance of the layers from the computer communication we can talk about, because ultimately wireless is one aspect of it between the device and the base station. But the chunk of the technology starts in the north of the base station itself, means the complete ecosystem of the products that get connected to realize a service. So that point of time when we were wondering that is cellular network is, and we all debated that it's all OSI driven, non-OSI layers driven, what is needed, what is not needed, actually. And we have come across from the GSM when we back in 1999, we went to the GPRS days, and it's the first internet, very low speed, complicated network with respect to realizing just about 56 kbps to 100 kbps of data rate on the mobile. We are very excited, actually, when we start putting our first browser, when we see the GPRS connection. It went to a humongous task of the protocols and algorithms to make a packet flow consistently from those so-called internet to our mobile devices itself. From there onwards, the internet, where I think when we talk about cellular, they were mostly governed by the body, what we call the 3GPP. And before the 3GPP, it was the GSM-A who was driving it. And later on, it became a 3GPP driven body where all people came together and the patents and the standardizations evolves by this body. So it's a group of community people that we started from the GPRS. It went to 3G, came to the 4G. Its a vision got changed drastically. We have seen and realizing it. For the last 4 years now, the 5G been part of the in and out, because my role started coming there, because from the standards, a lot of things that governs our system doesn't make to the product unless there are certain binding elements that we need to put forward. So that is what we call the system engineering, actually, where we start building and filling the gaps with the hundreds of the algorithms that needs to be developed, where the standards never get into that, actually, because standards decides the overall boundary aspect of it. The internal aspect of a system and its connectivity is a huge challenge and the scope for realization to a deployment, actually. So in same thing I'm seeing now in the 6G, that when we have seen some aspect of the 5G deployment, and that is where my talk will be aligned to, that bit by bit from the 2G or from the 3G to the 4G to the 5G, the network has converged to a lot of levels, actually. Now, whether it's a good, bad, that time will tell. The realization of the application will tell. But it's most in a hyper-convergence network that we are living now, actually. And I'll give you some glimpse of that, actually, how that convergence slowly bit, where we have married the 3GPP technology with IETF, with the DOCSIS. A lot of places we have done this marrying that has gone beyond the purview of the 3GPP aspect of it. So when we call a 5G, actually, it is not only the wireless, again, I'm spelling it out. It is the end-to-end realization of the products to carry a single packet from the source can be anywhere, back to the device and vice versa, actually. So the convergence of the network has happened. Complexity has grown tremendously, actually. One view of only the 5G network architecture I'll bring forward here. You can just see that how complex an operator will be deploying it. Beyond that operator, that internet wall starts. And that is itself is hyper connected now. So in this world, if I try to bring forward a 6G concept, where it will fall into, actually, like, are we overdoing it, or are we want to simplifying it? That is the debate when we start designing from the network point of view. The technology is there, technology will evolve. But the question comes, is the relevance of any network infrastructure to the network connectivity in the north of any base station? So we started analyzing it, some part of it, and 6G challenges we are thinking. The initial KPI, the key performance metrics indicators with which we want to give little heads up to us, that already defined by ITU, if you know that from the 5G world, that is already been taken care of it. Some technology components where the researchers are been focusing on, and the major component that we are trying to put forward is what I call as a lean communication layer, actually. You will see that the communication layers, if it is not simplified, a lot of this redundancy based approach starts coming, and that is covered up by one algorithm, by top of that another algorithm. So it means that if in the current 5G also, there are bundles of algorithms who are working in tandem, very complex algorithms, and working all these algorithms firing at the right instant of time is itself is a humongous task to synchronize this algorithm. So that is what I was thinking, that the time has come, or time will come, where we want to make a lean communication layer itself. If it is not lean, we end up in another complexity getting added over the legacy framework of our network communication and the wireless itself. So we add up another complexity to it. So in that aspect of it, we were thinking of the physical layer, because that is the first layer of attack, actually, in the sense like we have to think of from the researcher and the practitioner point of view. And we are thinking also that whether to come with a universal physical layer, because as we have seen now from the network, the physical layer have taken many forms of it, like be it from the wireless point of view, be it from the DSL point of view, be it anywhere. There are a lot of uncommonality and commonality aspect can be taken care of it. So that is where the scope of the physical layer we were trying to think, and we are trying to define the first line of division of our physical layer, that what it will look like actually. I'm not talking about the core aspect of it, like that I will talk about, the core with respect to the wireless, but in the wireline also we have to think forward. The access layer is the most critical layer in the whole communication till 4G and 5G we have seen it. And that plays a major role in defining, configuring, and making your packet really flow end to end. So this is the another two layers that we are all focusing very deeply here. And some of the scope and features that we are trying to, it will evolve actually. It is not that we have drawn and we know what will happen. But definitely the directions are being set forward in these two layers itself. And what we call as a cross-layer optimization between these two layers, how much of cross-layer can be taken, who will own what part of the scope, which features will be very much centric and which can be offloaded to another layer in a lean communication aspect of it. That is the big scope of our network architecture design itself. And from there onwards, we start defining the standard, we define the algorithms. That is the way we normally proceed to it. So end to it, we want to see that whether we want to add up the same complexity or the simplification aspect of it. This is my first slide where we are all sitting.
Sorry to interrupt. Can we change the slide orientation, sir, and make it full screen?
1 second.
So yeah, no, yeah. The first option, I believe, yeah.
First,
yeah, swap presenter slide.
Is it okay?
Yeah. All
Okay.
good, sir. Yes.
Yeah, thank you. So this is the where we are all sitting and giving the first.
Sorry to interrupt again. I think you need to minimize the WebEx window which is opened on top of the screen. I think it would be a chat window or participants window, or move that up just below.
Just below.
There is a yeah, that one. Yeah, you can just move that up. All right.
Is that?
Yes, all good, sir. Thank you.
Okay, so this is where we stand now, in the sense like a network that has evolved. If you see my rightmost slide of the whole aspect of it, you just enable my pointer here. So this is where we have the terminal, the access, the transport, the management, and the service plane. This is where the complexities has been added. We have added the wireless and wireline to it. So think of the network of the cellular. This is one aspect of our network. When we talk about cellular, it also has the broadband aspect of it. It has the home FTTH version of it. It might have the satellite broadcasting to it. And top of that, we have the transport. That is the guiding principle where it is connecting the different mechanism of communication across each other with kind of IMS or the top layer, what we call as the service layer itself. Now, this is where we are all talking, because I'm taking this call from my laptop. Somebody may be taking from the cellular, but we are all able to communicate. Now, so far, so good, actually. So is this the network? And even 5G is also one part of it, because I just mentioned the cellular aspect, 2G, 3G, 4G are all embedded into this part of it. Now, so far, so good. So now question that comes here is that, is this the convergence that we have already laid down for the last 30 years now, whether any packet communications that we want to initiate between a cellular to the broadband and vice versa to any of these things, how complex that if the 6G will do it. What is the access mechanism for each of this role to play? From the cellular access to the broadband access, whether we want to take up the transport optimization, or whether we want to do it from the service layer aspect of it. So it starts from the beginning that do we need to rethink this convergence aspect of it from the bottom up or from the top down approach itself. So the way the ITU, I'm just taking one snapshot view that the way the ITU has been defined, this is a well-known slide for the last so many years, people have presented it. It gives a paradigm shift actually, where we started thinking and integrating the application end to end, in the sense like we defined the broadband actually from the wireless point of view, but how this broadband will be realized from the internet world is also has to be taken. Then a lot of optimization has already been done through that actually, where when we are talking about in a wireless device, I want to see control plane or user plane latency or the high throughput. If the packet doesn't enter a wireless network, then nowhere I am able to realize any of these metrics that the ITU is defining it. So this is where it is not only the optimizations of a wireless, but we have been doing the optimizations across the surrounding elements of the network itself. Surrounding means a wireless network surrounded by the IETF wall itself. So this is where the handshaking has happened, and way the ITU has defined with respect to the peak data rate, the user, the spectral efficiency, the latency aspect of it, the density, though we didn't launch the density with respect to the massive IoT connection, but some bit of the realization from the 4G and BIoT and something we understand. Now, this is where we are trying to think forward that how this picture will look like, whether ITU and the recommendation will be given, that how this picture will be migrated from KPI and to support point of view to the next available aspect of it. Now I'll talk about what is the next available aspect actually. So applications from the 5G, it's a shift that happened where we have defined and started optimizing from the application by application itself. Like we've taken the mobile broadband as a top level service. Within that service, which are the applications needs to be taken, whether it's a gaming, whether it's a YouTube browsing or whatever. So these have been falling under, and we started optimizing the network, taking the service as a overall pipe. And within that pipe, each of this application behavior, we have started doing it. And that is where the realization of this algorithm starts happening day by day. We have come to the shape, that's what the deployment of the 5G has given the confidence now, that how the end-to-end packet from the source, maybe at some part corner of the world, traveling to the IETF standards, entering to the wireless domain or the wireless operator domain, and realizing from the mobile you are viewing it. That part of the optimization, we have already done it. Now, the second big optimization we are finalizing at the last mile is what we call as the URLCC itself. Where we have seen the remote surgery, connected cars, a lot of these applications has been packed under that heading called URLCC. The third part, we are yet to come to things. Things are going on now. Now, why I'm talking this, one is that the view of the pipe, the service pipe, remember the service pipe in my first convergence part, that we have taken the service into account and the application as my optimizing factor and started defining my networks actually, or the network standards and the algorithms. So that is where we are doing till 5G. Now the question comes is that, did we miss anything out? Is this the right approach from the top down? Can't we look from the bottom up? So these debates is now going on, that is going on. And just a snapshot of the deployment angle from the 5G network. One aspect of it, don't want to get into, you have seen it n number of times, but the base station, the access part of it, this is where the wireless, but just to give a glimpse is that these boxes that I have marked here plays another vital role with respect to your authentication. If authentication takes a lot of time, then it means that your surgery may get delayed. If your access and mobility in the core network doesn't happen at the right time, your control plane latency is severely affected, and your data will never go through actually from the user plane itself. That is from the data to the UPF world where the packetization happens, going back to the access world. So this where the complexity, if you're seeing it, when we see from the network architecture, this is one snapshot of my leftmost view of my convergence aspect of it. There are other rightmost view where from the satellite is there, from the broadband aspect of it. That is, I'm not getting into it. I'm just focusing on one aspect of the 5G network deployment and architecture. So here, if you see, each of these boxes plays a very important role in defining what to be done and how to be done, at what time to be done. Now, question is that if these things has to be done in one shot, actually in the tandem, then comes the complexity that are we meeting the KPIs or not? And somehow at this point of time, we are meeting it. But now comes the vision statement that in 6G, do we have to do in the same order that we have done till now? Question mark. We don't know. We have to think of. Now, this is where we have seen the pain points actually. Now, the pain points till 4G, we have all been worried about actually. 5G has solved some pain points. I'll not say every pain point has been answered. Some of the bubbles, if you see small, big, are still there. I didn't able to write it. But the main pain points that comes whenever you think of and converge an operator deploying something, like any operator who has a broadband solution and a wireless solution connect to the internet, the connectivity deployment is very complex actually. It takes time to roll out a network. It is not that fast that you just have a box, switch on the box and it will start working, because a lot of this intelligence is still manually fed. And what Dr. Lalop was talking about, the XAI actually, part of it. So a lot of this intelligence is not built in actually. It's that we are thinking to build in. Very small steps has been done in the 5G deployment. More to come. But the question is that the connectivity deployment is the key crux of any operator to worry about of this gamut of the network. The next part is the multi-standard actually. Like we talked about, not a single standard actually, because there are a lot of this standard that comes from the transport plane aspect of it. So wireless is not only now the access and the aspect of it, but we have to worry about how the access now communicate to the wireline protocol and the standards, the IETF wall itself. So those also has been there actually, and some part we have solved using the network slicing in the transport network itself. So we defined the way the packet has to be routed via router so that he sees a seamless virtual path with a certain amount of the prioritization, the same way the path has been defined from the wireless by the scheduler to the device itself. So it means that the slicing solved some aspect of our multi-standard protocols, but it's a problem to be addressed actually. It is not a small problem, but it's a larger problem in the context of the deployment angle. We need to solve it. The device is another big chunk of it, because this is your end point, the service end point, what we talk about actually. And this is where we visualize the quality of experience actually. The service is with respect to the network, and the experience we see from the device is where you see and you judge a network actually, saying the network is very good, the network is very bad today, or something has happened to the network. Okay, let me change my operator itself. Now, this is where the device plays an important role. And in 4G, we have done something on the device. 5G is an enormous changes happen from the device capability point of view. A lot of intelligence we have packed, but remember, device, when we carry in the mobility, it's a battery operated actually. Okay, so whatever we do it in the device consumes, any intelligence we put in the device consumes a lot of power. That's the reason a lot of this overhead we have taken to the network. But going forward, do we need to put in the network will again go back to its complex days itself. So we cannot able to afford. So something we want to offload in 6G itself. What debate? We have to see it. The legacy interworking is another important aspect of it, because any operator in the network doesn't throw his previous network itself. So they don't start from a green field. It has to be there. Top of that, we say that, okay, let's have a gateway, how we interact between these two, the new and the old, how they will be talking, this very important aspect of it. And we think that how this interworking needs to be done seamlessly. Scalability is another big aspect of it, because 6G is a scale now. Actually, we'll talk about the scale. If it is a scale, very contradictory statement is how you maintain, because in that scale of network, you cannot run 1 billion people to solve every 1 billion tickets that will be raised. So it means that maintainability has to be done in a seamless, automatic manner, and with a reliability aspect of it, because any of this reliability doesn't work, the network will not be able to deliver your service. So this is the deployment challenge that we need to solve it. And the question now comes that, again, we take the top down or bottom up, question mark. We'll see it, how it revolves to it. Now, this is the first statement that when we started thinking from the 6G aspect of it, 5G given the precursor aspect of it, that connectivity is very important. We have connected a lot of things now. What we need to do in the 6G is to take that as a baseline and move forward to the next level. What we call is a connected to everyone actually. Now, what is this everyone? We'll talk about in the next slide itself. Like what we left out in 5G, can it be connected in the 6G? It means that from the operator point of view, moment you add connect everywhere, you start sending the data packet, it's a revenue for the operator. So again, giving an example, when we had only voice connectivity in the GSM, we have very limited, because that point of time we had the landline phone, we had the mobile-based voice, we have options. Coming now in the 5G world, we have connected a lot of things. So if I'm able to connect more and more users or the more and more devices, machines, whatever, more packet flows, more revenue. So this is where the things that what we didn't connect in 5G can be connected in the 6G itself. Connect everyone, connect everything, everyone, human, everything, machine, everywhere in the world, wherever you find the gaps actually, or you improve the gap. You will talk about this, what we talk about, and connect every time actually, in the sense like, don't worry about the device, but whenever the device wants to send something or device wants to receive something, he gets an opportunity to transfer the packet. So that is where the every time means to the aspect of it. The applications we talked about, there's a known application of AR/VR of connecting everything. Space communication is where the main focus will be going on. The data center connectivity is another thing that we are thinking. Drone is already been some part being taken care by the 5G itself. The SCADA has been looked into very seriously. Cellular is by default statement. And the new one, what Dr. Alok was talking about, is the holographic aspect of it. So this is the application field. Maybe some more bullets will come as we move along. But this is what we trying to think and trying to see the experience of some of them in a current 5G network, in the sense like we have seen some aspect of AR/VR in the 5G. We have seen some aspect of the drone where we have mounted our base stations or the devices in the drone and seen some performance. Cellular is where we are very comfortable with. Now comes the next aspect of it, where the massiveness, the SCADA, the data center, and this holographic we have to connect now. This is where connecting everything. Now, what we have in hand, some of the vision technology for rendering, some of the cloud technology, what we have, satellite, optical, 5G++, what we call, that is the release 17 or 18 onwards, mobile edge computing, and the virtualization and the software-defined networking. This is what we have. Now, is this the stepping stone, or we need to add something? Next slide we'll talk about. Now, this is the first vision statement that after the vision statement, we were trying to think from the access point of view. Let's focus from the base station, because most of my work, all my years is in the access aspect of it, in the base station. So where we are trying to think forward that if I want to connect satellite to satellite, what technology we have, whether we can do it, or with air-to-air drones communicating to each other, just like a wireless mesh network. That is very probable, and cognitive I'll talk about will come into that is, and how we are adapting it, we'll see. This is the known one, the base station to the vehicle, to the mobile. This has already been addressed to some extent by the D2D the current communication system itself. Very confident we are now seeing the first level of the network rollouts, performance, and the trial network of the 5G. Living out the next part is the ship to ship, how we want to communicate. So now if you see that we want to expand, it's still a statement, how much we'll achieve it, the complexity, what is the physical layer complex we'll talk about. But the vision that we want to move on is that the space, the air, and the sea is what we want to see from the next level of the integration network, actually, what we call as the integrated network, actually. So network that we have seen now, that if I want to have one chat between my laptop to a person sitting in the ship, and he's able to communicate, that is fine. I am able to do a ship-to-ship communication via some mechanism. It's like kind of a D2D aspect of it, what challenges. So this is what the integrated network vision, that is the first guiding principle of to come out. Then what we did is that the next level, it's still a work in progress, that whatever the data rates that the 5G characteristic we have defined it with respect to the ITU, with respect to the trial network, we know some values that we are trying to achieve it in the like a zero mobility type of thing. We have already achieved and giving a throughput of 1 gigabit per second, and it's a reality. Like without any mobility, if I stand and have a kind of line of sight with my base station, average throughput of 1 Gbps is achieved actually. So it means to the fact that in my home, I can start thinking differently now actually. The cell throughput we have already achieved to some bit of numbers close to 10, going to the perfect number what ITU define it. Latency we have characterized it, control the user U plane means user plane, that is where your YouTube data latency from internet world to back to your device world, accepting it, vice versa. We have characterized it. Now comes the fact that the 6G, what number we want to look for actually. This number is not frozen to the level, but some kind of statement that suppose I go with a 10x or I go with a 100x values actually. So this is the debate that is going on, and whatever the number that comes, some number people are publishing it, and we are trying to judge these numbers, saying that taking the use case by use case approach, again going from the top down approach. So 100 gig part of it, terabyte, less than 0.1 milliseconds. Less than 1 control plane latency. It means that you are setting up your session less than end-to-end, less than 1 millisecond. It's a big jump that what we think of. Mobility of an aircraft up to 1,000 kilometers per hour where he's using 6G into it. The spectral efficiency top bound actually. So this numbers I'll not say is very solidified, but this gives the guiding principle. When we start taking any technological leap forward, we start thinking of that what is the number that we want to think of actually, and then starts the reverse part of it, that what research to be done. Then we started thinking that what we have in our hand actually, like when we're talking about 6G, that do we start a jump start from the millimeter wave? That is what we have seen now from the 28 gigahertz performance. Some of the worldwide operator has been showing it. This gives some bit of the jump start that how a millimeter wave at 28 gigahertz perform, but doesn't mean that it will perform at this level itself. So it depends its own characteristic based on the channel through which the communication will happen. But it gives that the fundamental aspect of it, that the range of the spectrum in which we want to move on and where we want to draw a line, with respect to the selecting the spectrum for communication, and where we want to draw a line where we take the spectrum and associate with it respect to the coverage and application itself. So that is what is the big charter of our work that goes on, and we want to think forward that terahertz is the right band. VLC is opportunity, we have seen it, some bit of the things we have already seen it, but where to put in which application at what point is the debate that the network people have started doing it actually. Now, with respect to the range, whether it's a short range, medium, because again, the contextual aspect of it, that whether 6G cellular will be based on a combination of these, or we stick into one aspect of the terahertz. It's very early to say in that, but promising results has been shown in VLC also, but it has its own problem that we need to solve it. Actually, we'll come to that, how these two are the things. But as we are moving on, we think that these are the two potential candidates, not the final candidates, for making some bit of the network access mechanism to roll forward actually. The other things that we need to think of is that short, medium power consumption, network topology that we want to bring forward. Because remember one thing, the fact is that though we talk about device to device, D2D and all that stuff, the baseline of the cellular, again, the concept is a point to multi-point. It means that one base station talking in a cell or through a carrier is happening through a multi-device connectivity. So these things we need to think forward, that seeing the characteristic of this spectrum that we have seen physically now, not experimental, in the physical communication world from the 28 gigahertz and going forward from the VLC, we now see some bit of the relevance, some bit of the scatterer information. So we need to think of whether how the topology will look like actually. Where is my noise source? This is very, very important for the physical layer guys to take care of it. And the weather and the security. I'm not getting into security, but part of these things comes as a driving principle. The first driving principle to fix the heart of the communication is wireless. Is that the RF actually, or radio, or the first aspect of it? Then comes the upper layer of the physical layer itself. So this is the vision that we are moving on. But the candidates that we have picked up now is the higher band of the millimeter wave to start. We are still not jumping directly to the terahertz one, but the higher part of the millimeter is the starting point to it to start, because of the silicon and the silicon technology availability aspect of it. So part of this one, the devices is been in the lower part of the millimeter, the device is already there in place. The higher part of the things we have to see, research from the device and the silicon, the solid state physics aspect of it has to be frozen before we start integrating to a product actually. Now comes the challenge actually. Now, giving the first aspect of it, the first thing is the convergence aspect, that the service, universal service convergence, whether we want to do it in the sense like, do we still want to have human to human, human to wireless device anywhere actually? Now, this is where we are thinking that seeing the 5G's performance, that gives a jumpstart and confidence that we are able to actually converge the application, whatever, from the human to human and human to any device, machine to any device. This is a realizable entity in the sense like we can able to certify the statement saying that yes, this has been proven. How it will evolve to with respect to the next level, but some bit of foothold that we have known from the 5G's experience. The next part is that we are trying to attack from not taking all the applications one shot, but we are trying to see with respect to some bit of the application where we are putting back from the extreme throughput aspect of it, because the holographic type of application requires tremendous amount of throughput actually, and tremendous amount of the channel information amount, knowledge itself by the either side. So extreme throughput is what we have taken as one of the example to start analyzing it. URLCC is, I'll not say URLCC what 5G has given, but what I could have done called URLCC++. It's the next level, a flexible range and the zero power at the first level of my application. Not everything in the bullet as I talked about, but it's a starting point to understand and realizing that which are the elements we want to keep, which we don't want to keep. That is the first level of our understanding. The third thing that we are putting as a proposal is that 5G never has been intelligent enough actually, in the sense like, okay, we can argue the point that algorithms are intelligent, but the intelligence with respect to the self-organizing with AI and ML is not being there as a formal standard. In 5G, we have added the virtualization and NFV into account as a formal ITF to get into the main standardized coherence from the ITF to the 3GPP world. But now we are pushing forward that intelligence with respect to some form of AI/ML needs to be there as a formal entity to look forward. Moment you bring this intelligence, a lot of these things will be picked up by the operator because they are really struggling with respect to deployment aspect of it. So I want to make an end to this heuristic and algorithm-based approach actually, because I'll not say that end will come soon, but the algorithms world will start diminishing slowly because it will be more constructive than the algorithm. When we say algorithm, it is preconceived and then tested, because we build on maths, we apply the maths to the simulation. Simulation goes to the product. Now the question that comes is that if you go in that approach of the development cycle, it is a slow and it's a big burner into it. So we need to think that algorithm has to be evolved from the intelligence that he will be gathering to it actually. So it is more adaptive than given by the system of the policy governing that algorithm. So he has to adapt himself. So end of this heuristic aspect, end of the legacy or the way we're doing it, aggressive cognizant system that we want to bring. And this is what I will talk about very shortly, that what is this cognizant system will bring it. Very important aspect of it. Like for example, I given a very small example that will solve this aggressive cognizant application. We think that network will honor me every time I switch on my mobile, and I think that I need to get connected because I paid my service. That is the demand that you have taken from an operator. So you think that the operator will give you service immediately. That is when and the procedure starts. The self-service procedure starts. The synchronization procedure starts, and it's the back end of this part of it. But do we need to see that if my device is trying to understand that, and whether my network is able to do it by some mechanism itself? So there will be some amount of cognitive approach to figure it out, that whether I want to give you a service or you want to take a service from me actually. So it means that moment this system comes into play, immediately your characteristic of your transmitter, whether you are a device as a transmitter or base station as a transmitter, will start adapting yourself. It's a concept, and it's a wide concept that we have seen from the cognitive aspect of it, where the cognitive spectrum sensing is a lot of work has been done for the last 7-8 years into it. Some aspect of it we want to pull it back to our adaptive aspect of it, and what we call as the pure zero touch aspect of it. So it means that we don't want to really configure and doing everything. Like nowadays we tell that, okay, this parameter value X, this parameter value Y, this parameter value Z. It is again a painful exercise. So how can we make a perfect zero touch aspect of it? So this is what will be part of the standard we'll be pushing on, calls how adaptiveness, we want to bring it back to the system. The next part of it is this thought that we'll be pushing hard is what we call as a lean communication layer actually. So the layer I didn't talk about, if you can see any standard of 5G or any standard of our ITF, it's a heavyweight standard with respect to its physical layer from the Ethernet world, with respect to have their own access mechanism, with respect to an application top of that. 5G also brings its own physical layer aspect of it, own more in this access control itself. There are bundles of the layers that has been put forward, and each bundle layers has its own algorithms to work actually. So now the question is that how can it be more leaner now actually? This is the coin that will be going on, that application has to be lightweight for short and secure, redundant and rendering aspect of it. Because if I am able to manage here in the lightweight, a lot of my overheads that goes below down in these to this becomes very lean aspect of it. Because to make my application layer quality of service to maintain, we keep on thinking, saying that what will be my MAC, what will my scheduler, what will be my radio resource, how my OFDM grid will look like, how the channel model will behave my grid to change. it becomes a lengthy research now. Now, if I make my application become light, how light, time will tell. But this is the thought process that will become a back pressure on my cross optimization layer to comment into it. So we are trying to think forward that the scheduler, the mobility, the grant free, a lot of these things, there are multiple bullets. I just picked up some of the important aspect of it. Needs to be relooked and rebacked actually, in the sense like it has to be thought through in a much more holistic manner, because I want to make my application centric light as much as possible actually. So thinking this layer, we want to now see forward that what are the changes that we want to bring back into the packet control and my physical layer aspect of it. What candidates that come thinking from this layer, because 5G has given me the confidence with respect to the smart city, with respect to AR, VR. So going forward, this will be the stepping stone of it actually. Now the components that still it's the list is little longer, but then the shorter length of it is that the candidates I talked about, that when we think of the physical layer, the communication, the actual heart of my wireless is via terahertz or VLC. We have to think forward which is the best one to take for what application aspect of it, with respect to the new efficient waveform actually. Now this waveform is the first line where we're trying to define the radio resource actually, whether we go with the proven grid that we have seen, the time frequency grid, or we want to add the next part of it. I'll talk about what we are thinking of adding, the space, the third metrics to it. It's a time, space, and the frequency. This is where the waveform definition will start evolving, and people are thinking that what will be the waveform to become, and what measurements and the mobility that each of this will short, because it has its own coverage with respect to limitation of its propagation. So what measurement, how mobility will be taken care. The next part we are talking about what we call as a cooperative massive MIMO actually. So the current transmission, if you see, is very centric, like the base station having its own MIMO. But the question is that when a device is actually seeing a channel, the channel can be seen differently by the different angles of my transmission and scatter itself. So it comes to the fact that today we do what we call as a coordinated multi-point transmission is one of the big features of our cellular communication, where base station to base station is talking to each other to sending a packet with a zero packet loss to the device. But we are not into the cooperative massive MIMO in the sense like which element of the MIMO of the second base station to be excited by the packet to move actually. This is what we call as a cooperativeness actually. So more coherent reception that will enhance to me, more waveform predictive reconstruction will happen actually, in the sense like this predictive reconstruction, like what happens in our world is that we spend a lot of time in correcting with a lot of this channel estimation and equalization algorithms actually. A lot of time goes in that actually. So some bit of these things loosen up or makes our life easier when we start doing what we call as a predictive reconstruction actually. So it means that the waveform helps me to do that prediction and reconstruct the wave rather than going with a multiple hybrid ARQs and all that complicated aspect of it. Then we are trying to bring forward the channel sensing, what we call as the digital signature of the channel itself. Now, it's a new coin word, that is we are already doing with certain amount of the reference signal. And this is where we want to enhance truly, saying that the cognitive aspect of it, that the digital signature based approach where the feedbacks will lead to the fact that my radio conditions in where and what type of my mechanism to be taken for what type of application that I want to initiate actually. So this channel sensing is what we will be focusing in very, very deeply actually, with level of the service and the radio architecture with respect to the fact that how much of the end-to-end point with vertical and horizontal scaling that we want to do, decoupling the transport and the service layer itself, that's some bit of the optimizations that we need to do it there itself in the first core, and what we call as a dynamic association aspect of it. This is where the most of the self-optimizing network will start evolving it. That is not been seen truly in the 5G world, but in the 6G, what we want to see is that based on your characteristic of these points, the transport mechanism can change. Maybe I call it like UDP suddenly become TCP and TCP becoming UDP at certain point, short TCP getting triggered. So a lot of this decoupling of and dynamic association will start happening it. TCP UDP, just an example, in 6G, you don't know what will happen, but just to tell you the glance that our thinking process, that how we are trying to decouple and make a dynamic association of my transport and my service layer. And I talked about this adaptive network deployment. Start with default, and based on learning, we adapt. So this is where things will move, and we want to put back the learning back to the standard. And the constant cost optimization with respect to the path of my packet flow. Remember, the packet stops at the service endpoint is my device. My service start point is my one server in part of anywhere in the world. That whole packet path, what we call, has to be optimized constantly. Any of these characteristics will undergo change. The quality of experience, choice of my backhaul and access and device programmability will be focus of that. And device programmability is where we'll be focusing much more, because we want see currently what is happening, that device is still looking for a lot of things from the network actually. So if the network, if you are not provisioning properly, the device behaves improperly in the network with respect to different counters, timers and all that stuff. So this programmability of the device will be a push forward in the technology components to come. Now, if you think that that is understood, then where my physical layer scope will move on actually. So the channel modeling is an important aspect of it. A lot of research, and our next speakers, Debarati, will talk about more in details on that model. But what is the base important from the network, from the base station, is that do I give a radio coverage to where actually? Indoor, not outdoor, or outdoor, not indoor? That dilemma is there actually based on what characteristic of my signal property is varying into my zone of my base communication, or whether terahertz or VLC or whatever we are trying to take. So frequency selectiveness is another important stuff actually, because when we say that the channel behaves and it has a dip of fading coming at certain frequency selective, if I know beforehand by the channel sensing and I able to adapt myself, this becomes much more efficient way of our communication, and to surpass some of the absorption mechanism that we see, the propagation of the symbols going through the channel itself. It solves a lot of my problem. We kept this frequency selectiveness by some mechanism in 5G, in 4G also, with respect to the channel sounding aspect of it, constant channel sounding, constant channel measurement, channel delay spread measurement, the channel Doppler measurement, everything we are trying to understand, the timing advance aspect of it. A lot of these complexities get solved moment I see something that is been known actually. The waveform definitions I talked about, the currently we have seen the efficacy of the time frequency grid. We are adding the next part of the space and the dimension to it. We are moving to the ultra massive MIMO. It is not only the massive MIMO. See, currently till 4G, we have a kind of trial deployment of 64 cross 64 elements deployment performance in the network. Means in the outside outdoor environment, we have seen its performance. Now, this is where when we are talking about cooperative MIMO, so where we are trying to take forward, it is not only 64, it's much larger dimensions what we are talking about, where we think that the channel hardness seen by one element is very applicable for the user doing some amount of application transfer, and in a cooperative manner actually with another base station taking something control and all that stuff. So this is where the massive research will be focusing on with respect to the cooperative and ultramassive MIMO aspect of it. The coherence bandwidth time analysis software defined fluid antenna. This is where the next set of things what we have been thinking of, that currently our antennas what we have solved with adaptive array system of the antennas that we have already taken into control from the access control mechanism itself. But the antennas are very solid in nature, in the sense like tomorrow, if I say the dipole can be taken by the microstrip can be fluided into having some form it other based on the way I'm seeing my channel. So fluidity of the antenna has to be looking into. This is a new thought process, and more work to be there, because this will be a game changer. What I felt is that coming out the last part of the antenna research, where we want to we are moving from the adaptive array performance to more fluid based antenna aspect of it. So this is a work of art to be taken in the future. Transceiver design is the heart of our software angle. The estimation, equalization, the modulations that we want to take, the code rate, the transmission power. But these are all known points that we have been carrying over from the 5G. 6G will take into the new dimension to it. But what we in the 6G that we want to propose, that has already been researched now for the last several years now, what we call as a spatial modulation. So this spatial modulation combined with the ultramassive MIMO will be one of the big things to actually realize what we call as a holographic communication at SIV. So this is where we want to see the how things will be realized. Some bit of the spatial modulations techniques, and with the current antenna system, we have seen the performance, but it's a long research items for the next couple of years. We want to see how this thing will be getting coherently working. We have pushed forward the AI/ML part of the 5G. Big data will be another aspect of it, because large amount of the data analysis, what we are trying to do now, unless the big data technology is there, we cannot solve it actually. What we are talking about, intelligence and all that stuff, this one cannot be solved unless we bring forward the formal aspect of the big data. That's where the cloud aspect needs to get into the 3GPP world. We have made the ITF getting into 3GPP world. Now the cloud technology has to formally get into the 3GPP world. And the physical layer security, nonetheless, everywhere we have to talk about. But only case that we want to bring forward is that the security layer that we are been talking now in the transport layer, the physical layer will now play an important role in making your secure combination. It's not only the transport layer and above where we make the secure communication, but physical layer has to think differently in making this communication. Now, access layer has its own challenge actually, because it's where it acts as a binding layer actually, in the sense like when we talk about the space, drones and terrestrials getting together, what we call as a super HETnet network actually. So this layer, what we call as a cell-free access actually, in the sense like, though we talk about textbookish approach of a cell, but actually our cellular world is not a cell level. We so call that, okay, one carrier frequency transmitting at some part of the coverage area, we think call as a cell, whatever mechanism, but RF cannot be controlled. But here what we kind thinking of is that there nothing will be calling as a cell totally has to be knocked out from our textbook called cell-free approach, where it's a single waveform with all connectivity in place. Like you don't feel that you are now connected via Wi-Fi than connected over cellular when you're moving in and out or something like that. So this is the concept that from the access layer research is going on, where the focusing of the cell-free access to it. And what we are focusing on, what we call as a contextual and cognitive aspect of it, where we understand the base station. It is more environmental aware actually, because if you want to go to the VLC and the terahertz type of things, we want to do an holographic aspect of it, of my channel, rather than more and more concentrated beamforming. It is the next generation of my beamforming, whatever means that we have been doing now. Like currently we have successfully deployed the digital beamforming now. We are now in process in the millimeter wave. We have actually did the hybrid beamforming, where both digital and analog has been punched into it. But going forward, we are very not satisfied. Actually, we want to just see that how the holographic aspect of my box of my channel, seeing by the device and seeing by the base station, is more environment aware actually, so that we can change more adaptive way. Scheduler will have its own journey of its algorithm based going back to the AIML. It's a new things that we have already seen in the 5G world. It's not deployed in the sense like AIML based scheduler, but how the behavior of the scheduler will happen. Some bit of the papers has been there. Actually, we have experimented that part itself. But more will happen going forward in the 6G, where the full-blown manner of the AIML into the scheduler will be placed to it. The mobility will be taken care by multiple different access, because we are talking about the multiple mechanism of connectivity with space, drones, terrestrial, and all that stuff. Listen before talk will be the fundamental aspect that we want to put the cognitive into it, and how you manage the space-time grid into is myself. We talk still space-time, but it is still not been endorsed by any standard that we have to actually add space to the time and frequency, because 6G, we are still experimenting, trying to see the first level of the research that does the benefit of my OFDM grid, kind of, if you add space, that makes sense. But tomorrow, this point can be totally overwritten by some other means. We don't know, but still the research that we have started to figure it out, whether it makes sense or not sense actually. So if not, something will come up actually. But this is where the concept of the access layer, the lean access layer, where more contextual and cognitive will be start putting into it. It's a big amount of the definition we have done it. So question that still comes, and I don't know how much I have tried to answer, but the question still remains. It's like simplification of the complex network architecture. So we are still figuring it out, seeing from the 5G aspect of it that, see, whatever research we do, ultimately we have to make a product actually. And without the compute fabric, whether it's like open source based servers or some dedicated silicons that is popping up, how it's shaping up my software angle. If you think of like whether my real-time kernel is taking care of doing my latency when the packet moves within my operating system, those things will start coming out in the network compute fabric itself. So this is the things that we need to work very closely with the vendors in ecosystem, that whatever we define, whatever the vision that we think that we want to realize, we want to first see that where this will run actually execute actually from the system point of view. Based on that, a lot of things that get crisscrossed actually, some things we stop, something we enable, and all that stuff. So on that fabric is once it's frozen, or once it's in due course will be frozen, or we know the path in which we will be moving, we want to deploy the universal connectivity. That is where my space, air, whatever the mechanism, because it also take into account from the network. I talk from the network point of view, especially say a base station having a network fabric, putting into a ship, running in the DG set, can able to do all this fancy communication mechanism or not, and do this universal connectivity, because the network compute takes a lot of thermal and other heat into it, not conducive to do a lot of applications. So this is the fundamental aspect that we think and we work forward. We think from once it is baseline, we start the universal connectivity, adaptability, device connectivity, the performance coverage and the cognitive aspect, and then we do the application harmonization. So this is where when we build a system, we normally go from the bottom-up approach, but when we actually start realizing it, we keep a little bit of broader vision from the top-down approach itself. So this is where we think that a lot of scope is for simplifications we want to attack actually in the 6G. This is the right time, because some leaner already happened in 5G. Going forward in 6G, whether how much lean we want to make it up. And we can see that, okay, some of these high throughput, high sensitive, ultra latency applications working on a compute fabric is able to deliver your quality of experience or not. That is the next level that we want to think going forward actually. So that ends to my talk here actually. Thank you for your time and listening to it actually.
Thank you, Dr. Saptarshi. Thank you for sharing so much in-depth explanation about the opportunities and challenges, not only from the RAN side, the transport core, as well as application side in 6G. So participants, two more interesting talks are in line. So bear with us if the event gets stretched a little bit further after 1 o'clock, 15-20 minutes. So, but I'm sure this will be worth spending because of the knowledge that you may gain by the end of the event. Now, to take us forward, I would like to request my friend Deborsi to take us through the subsequent sessions of the event. Over to you, Deborsi.
Thank you, Bengaras sir and Chengappa sir. So we have two exciting sessions aligned us today. It's coming. So I'm extremely thankful to Professor Sudhir Mishra sir and Professor Devatishan ma'am for accepting our invitation and giving their valuable time and knowledge to us. Obviously, the speakers are extremely well known for their noble contributions and they don't need any separate introduction. But still, to begin with, I would like to introduce Professor Sudhir Mishra sir very briefly, who will be talking on synerging IoT with 6G, applications, challenges, and scope. So Professor Sudhir Mishra is a professor and INIE Abdul Kalam Technology Innovation National Fellow in the Department of Computer Science and Engineering at the Indian Institute of Technology, Kharagpur. He received his PhD degree in computer science from Carleton University in Ottawa, Canada. His current research interests include wireless sensor networks and Internet of Things. Professor Mishra has published over 350 scholarly research papers and 12 books. He is a fellow of the National Academy of Science, India, Indian National Academy of Engineering, the Institution of Engineering and Technology, UK, British Computer Society, UK, Royal Society of Public Health, UK, and the Institutions of Electronics and Telecommunication Engineering, India. Professor Mishra is the distinguished lecturer of the IEEE Communication Society as well. So thank you, Professor Sudhir Mishra sir, for your time and acceptance of this invitation. So it's over to you, sir. Thank you.
Now, okay, so thank you. So am I audible?
Yes.
Okay. Okay, so thank you, Deborsi, for that nice introduction. And at the outset, let me thank again the IEEE Bangalore ComSoc Bangalore chapter, as well as IEEE Kharagpur section for organizing this session and also inviting me to deliver this particular talk. So since the morning, we already heard some exciting talks by Dr. Aloknath De and Dr. Saptoshi Chaudhary, and so it was like we got a lot of knowledge. It was an ocean of knowledge that we have been swimming in since the morning. The advantage of speaking after these speakers is obvious that I do not really need to continue for too long. I will be very precise. I will try to finish my talk in 20 minutes to half an hour maximum. And most of the things about 6G have been already told by these experts who are actually, who have got their hands dirty with 6G. For me, actually, my focus in the in the SWAN research group where I have been working in IIT Kharagpur, my focus has been mostly on IoT. So today I will take the perspective of IoT in this overall workshop on 6G and try to see how IoT and 6G synergize. So the way I see is that IoT is something that is coming. From IoT we are gradually getting into massive IoT, extremely massive IoT, and now people are talking about Internet of Everything. Different leading organizations like Cisco, etc., have already given their vision about Internet of Everything. So IoT, IoE is something that is happening and is coming in a big way in the future. So the problem with IoT expansion, I mean, IoT is inevitable, but the main problem, the main hurdle has been from the technological viewpoint. So one of these has been the communications, because most of these envisioned Internet of Everything aspects basically require a very high performing communication backbone. Now, with the kind of research that this domain of researchers in 6G have been doing, the way I see it is 6G is going to basically solve some of the problems of IoT in future. So in a nutshell, basically, 6G can be thought of as one of the enablers of IoT, IoE, massive IoT in future. So we in our country, we have been witnessing since the last decade or so the massive expansion of smart city projects. So the government started its vision with the 100 smart cities being identified. Then phase-wise, different smart cities have been implemented, are being implemented. And the main idea is that how you can improve the overall quality of life of the citizens. This is one thing. And in parallel, there is the manufacturing, the industries, the smart factories, the smart industries. That is actually part and parcel of the overall structure. So together we can think of as smart infrastructure, which basically is something that we are all evolving in the country and abroad. We are transcending towards a society where there is going to be smart infrastructure. Smart infrastructure will have to be built, which is going to improve the overall quality of life while keeping in mind about the required cost reduction in terms of the technological expenses and the expansion, and also the overall efficiency of the systems. So all of these are basically happening at present, and in the next decade or so, we are going to see a massive expansion in terms of the smart infrastructure, that means smart cities, smart industries, and so on. So everywhere in each of these different domains, there are a lot of research works that are happening. So what you see in front of you is basically a classification of the overall IoT ecosystem, the overall space of IoT, which the machine-to-machine communication is basically a part. So I'm not going to talk a lot on machine-to-machine communication, rather stay focused on the 6G and the perspectives of IoT for 6G. But essentially what is coming in future in terms of IoT is basically this machine-to-machine communication, which is going to help in building fully autonomous communication interfaces, which is going to help in the expansion of the IoT ecospace. So as you can see in this figure, I'm not going to elaborate further, but as you can see that in terms of whether it is the service sectors, whether it is the application groups, whether it is the locations, whether it is the devices, we are actually, the whole world is gradually transcending towards a massive kind of smart connected infrastructure where there is minimum human intervention. There is almost fully autonomous machine-to-machine interfaces which are going to be operational. And as Dr. Saptarshi Chaudhary was telling earlier, so the way we see the future coming is Earlier, we used to talk about, connectivity of everything, everywhere, every time. And now we are also talking about everyone being connected. So you see, everyone, every time, everything, and so on. This is kind of a big, kind of complex infrastructure that will have to be built in order to realize this kind of vision. Now, when I say this, and as I will talk a little bit more on this also, we are not only talking about ground level communication, we are not only talking about underwater communication, we are not only talking about aerial communication, we are also talking about space, interspace connectivity, so space, air, ground, and water, underwater. So all of these are going to be all connected, and that is what Dr. Chaudhary was talking about earlier, right? So this is going to be a complex, a very, very complex system, not only due to the scalability aspect, but also just imagine how much of complexity is involved in terms of the disparity that is going to be taken care of in terms of enabling this end-to-end kind of connectivity. Think about a device in space being connected to a device underwater. Let us say a drone which is flying in the air being connected to a submarine. And this is something that is required, right? So if you think in terms of military, for example, right, and integrated defense forces, basically this is what they envision to do anywhere in the world. So in our country also the same thing, right? So whenever we are talking about military exercises involving army, air, navy, etc., so this is what basically is required. You need to have the drone, that particular thing, which has that Raspberry Pi, which is on that particular drone, connected to the Raspberry Pi in the submarine. Now, see, if you think in terms of the physical communication, the complexity is huge. So first of all, already just forget about all the other layers, just, aerial communication, that itself, drone to drone communication, it's a very complex exercise. In the SWAN lab, in the last about a decade or so now, we have been doing a lot of work on drone to drone communication. We have been, we have prototypes, etc. But let me tell you from my own personal experience that it is extremely complex due to number of factors, which I'm not going to elaborate further. But if you are interested, get in touch with me offline, and I would be happy to discuss further on this. So drone to drone communication, forming a mesh structure, a mesh network of drones, right? We have been working, we have been successful to some extent, but there are huge challenges that are added. The same thing, submarine to submarine, we also have executed different projects, government projects on underwater communication. Just the underwater itself is quite complex. Now you are talking about the drone to underwater, how you are going to make things happen. So where is this communication support that you are going to get? Because the existing ones, basically, they have a lot of challenges. And most of these applications, they require real-time guarantees. So where is this integration going to happen? How it is going to happen? So for this, 6G already, has made some kind of visions towards this kind of, ecosystem that is going to be realized in the future, and a lot of works accordingly coming into picture. Another thing, let me give you a little bit of idea. I think many of you have seen some of these sci-fi movies where there is holographic, holograms, right? Holographic systems, right? So you have some kind of a mass transfer or something like that in front of you, where the person to whom you are communicating basically kind of comes in front of you, talks to you, and then it disappears, right? So this is what many sci-fi movies or things show. But this is something that is desirable. It may be sci-fi for now, but this is something that is desirable. And holographic teleportation is something, a technology that people have been working on, which is important to make these kind of things possible. let me give you another thing which is already happening. So this is basically brain-computer interface, right? Nowadays, a lot of work in our department also. There are researchers who have been working on brain-computer interface, BCI. So now what happens, most of these research works are talking about that how the human brain can instruct different devices, IoT devices, right? I can, if my brain signals are being analyzed, I should be able to turn on or off a particular machine, right? I do not have to really physically go and turn it on or turn it off. The machine is there somewhere in San Francisco. I am sitting in Kharagpur and I want to turn it off. It is running over there, right? All I need to do, I don't need to really go over there. I don't need to do anything. I will just, my brain signal will be analyzed. I just have to think in those terms, and the corresponding action is going to be taken. So these are like, futuristic for now, but these are happening. So BCI, another aspect is basically, so I was talking about brain to device, but device to brain. Can we have devices which are going to instruct our brain to do something, right? So both ways, basically. That is even more complex. But the beauty is that these things are coming in future, and we have to make it happen. And we need 6G and beyond. Nowadays, I prefer to not to call 5G and beyond, because 5G is almost like here, almost, right? So we still have a couple of milestones to achieve, but so I prefer to call it 6G and beyond. Okay? So 6G and beyond probably will help us, this community, Dr. De and Dr. Chaudhary and those who are working on 6G. So Dr. Sen, Devarati Sen. So these are the guys who work a lot on 6G, and they are going to make it happen, right? And throughout the world, there are many others. So you see, this is one aspect. Another aspect is AR, VR, augmented reality, virtual reality. We are talking about AR, VR. We are talking about drones, SCADA, then what? So in terms of communication like VLC, right? Visible light communication, in terms of mobile edge communication, SDN, NFV. So these are all like technologies which will be required in order to make things happen, right? So these are all of these different things. So Dr. Chaudhary and both of them, they talked about many of these different technologies, how they could be, they could be made to work together in order to basically make things happen. So going forward, let me now talk about a little bit of what I was telling you earlier. So so in terms of the evolution of IoT is evolving to IoE. So now we are not only talking about people, process, data, but also things. So everything is going to be connected. So we are basically going to have this ecosystem where people, process, data, and things, all of which are going to be connected together. So there is going to be full automation. There is going to be full automation. And the other aspect that is also very important is the energy issue. That basically runs in parallel, right? So energy issue, right from the days when I used to do a lot of research on mobile ad hoc networks and sensor networks and so on. So energy efficiency is very important. And with the massive growth of IoT and interconnected IoT, so basically, this kind of thing, energy efficiency aspects are becoming even more important. So energy efficiency, automation, these are basically, these will have to be taken care of, right? I'll also show you one of, a couple of my students basically have worked in the past and are also presently working on something called nano biosensor networks, right? So basically, what happens is that you deploy a couple of sensors inside the human body and try to make these things, work with each other, and the signals are going to be taken out, and the person is going to be monitored, right? So in terms of therapeutics, in terms of diagnostics of human beings, these are basically very useful. So like this, actually, lot of disparate patches are there in terms of research. So 6G, one of the things that it will try to do probably is to basically help in the integration of all of these different disparate patches. So earlier I was also talking about this kind of space, air, ground, and underwater kind of communication. So in silo, these are important, very complex, lot of challenges. But what is even more interesting, and we have to make it happen with the help of 6G, is basically an integration of all of these things. So use cases where coming up with use cases, thinking of use cases where each of these are going to be all working together is going to be very interesting. So massive IoT, Internet of Everything, is something that is coming in future. So there has been there have been some efforts on something called Network 2030. So basically, where the network is going to be, how the network is going to be in 2030, right? So I'm not going to go through this this stuff in complete detail. You have it in front of you, but I would just like to highlight a couple of things. So in terms of verticals, so network basically, so what you are going to have in 2030 in terms of the overall network, and in terms of the different verticals like social and entertainment, healthcare, automotive, education, factories, all of these verticals and cross vertical, right? So how you are going to have these all connected, how the coordination is going to happen. So so all of these different technologies like tactile internet, holographic media, haptics, automation, in-room presence, and so many things are there. So all of these are going to be put together, and the network 2030 is going to be very interesting. I'm very eager to see it. Probably post-pandemic things are going to be much better, and probably so all of us will be able to see what 2030 holds for us. So basically, so multi-sense technology, right? So so far what? So we have been depending on touch, we have been depending on sight, right? Vision. So multi-sense basically talks about all these 5 senses, right? So we have touch, smell, then vision, then so all the 5 senses, right? Then hearing something. So all the 5 senses. The indriya, right? So all the indriyas, these indriyas are all going to be made to work. So holographic multi-sensing, holographic teleportation, brain-computer interface, brain interface, brain to computer, computer to brain, all of these different communications, all of these are going to be required, so that we are really going to get to a world, an exciting world, where there is going to be truly immersive experiences, truly immersive. The person sitting in San Francisco comes in front of me. So if I dial some number, comes in front of me, talks. So there will be some transfer of mass or something like that. The person comes, talks, disappears. Right? The world is going to be really fun, and 6G basically and beyond will have to make it happen. I mean, it cannot make it happen by on its own, but basically, so we have to all make it happen, and 6G is going to be an important enabler for it. So all of these are so far so good, looks very interesting, but think deeper in terms of 6G. Why we need 6G? Why we need 6G? So if you think about 6G vision as is being drawn globally, we are talking about massive scalability. And consequently, because of the rise in population, and also in terms of the connectivity of so many different devices that I just told you, we are getting into a world where there is going to be a device density of 100 million connections per square kilometer, and 6G has to support it. In terms of mobility, 1,000 kilometers per hour will have to be supported, right? Still, when I travel on my car, right, there are mobility issues, right? I get disconnected on my call, right? So there are mobility issues, but the future vision is that we have to support more than 1,000 kilometers per hour kind of mobility. In terms of signal bandwidth, already the previous speakers talked about it, talking about 100 gigahertz to terahertz, right? Or maybe even more, right? So that kind of signal bandwidth is going to be supported. Things are going to happen. Full coverage anywhere on the earth, doesn't matter. Even if you are in an underground coal mine in Dhanbad, you still will be connected, right? So so this kind of thing is going to happen, right? So 6G basically has all these different attractive promises. Timeliness in terms of the age of information, privacy, security, very important, and we'll have to be relooked into because of all of these newer challenges that are there. You simply cannot work with this kind of previous network security solutions, PKI, RSA, etc. So those are not going to be sufficient. You need to look into it. Even the current day blockchain, which I'm going to talk about shortly, that is also not going to be very sufficient. So like this actually, so a lot of attractive offering are being envisioned, and many of these are going to be required in order to make our life very quality of life very good in future. And this is what 6G has in terms of its promises. So 6G is envisioned to enable massive interconnectivity in IoT. There is going to be more bits and spectrum and denser network. There is going to be convergence of various communication systems. There is going to be convergence of communication, caching, computing, control, sensing. From network softwareization, which we are working on at present, the world is working on. Network softwareization is very important, a hot topic of research. Our SWAN research group also. We do a lot of research on network softwareization. So we are from network softwareization. We are, yeah, somebody said something. Okay. So from network softwareization, we are going to gradually get into network intelligentization. Network intelligentization, right? So softwareization to intelligentization, and from centralization to distribution. Already it is happening, so distribution, blockchain technology, this, that, so all of these things are happening. Yeah, somebody wants to say something? Okay, so let us go ahead. So earlier 1G to 4G, the focus was on people-to-people communication, person-to-person communication, 1G to 4G. 5G talked about IoT, people to thing to people, IoT being brought into place. And 6G and probably beyond is going to talk about thing to thing, fully autonomous, no human intervention, everything working on its own. A massive it's a big ambition, but it requires massive research, and it is going to happen. So thing to thing basically is something that we are seeing future. So what we need, all of these visions we need, how can we make it enabled? So 6G with all of its vision, like the ones that I just mentioned, are going to help in the massive IoT development and creation of Internet of everything, right? So what do we need? I said that network softwareization to network intelligentization, intelligence. So our friend artificial intelligence, AI, and also its partner machine learning. So it's all going to make it happen, right? So AI as a service is what people are talking about now. AI as a service, right? AI has become very much pervasive in the technological ecospace, and AI as a service is something that people are talking on right now. So you need AI for perception, you need AI for networking, and even you need networking for AI, right? So these are all there. And another two things that are also very important and enabling technologies are, number one, the edge intelligence. There is a lot of hype on edge computing, edge processing. So earlier people used to talk only on cloud, so dump everything on the cloud, right? So those days are gone. So it is still there. People are still practicing use of cloud, etc. That is there. But in terms of futuristic research, cloud is like we have gone past cloud right now. So people talked about fog. Cisco did a big work and envisioned about fog, etc. Many companies, including many of the participants, they have been working on fog probably from the different industry participants here. So fog, and then people are talking about now edge processing, edge intelligence, edge computing, right? So in edge computing, basically, all these edge devices are going to do a lot of these intelligence, this processing, right? All these intelligent algorithms are going to be executed at the edge itself. No need to send all to the cloud. Do some of it in the edge. Why? Because you see, you have promised that for the future IoT, you need, extremely low latency. Extremely low latency. How it is going to happen? If you want to send everything, there is going to be propagation delay. If you have to send everything to the cloud, that is not going to be feasible in terms of bringing down the latency. To bring down the latency, you need some of the edge processing to be done. So you have some of these algorithms also. Let us say surveillance, right? So one of the common use cases, in a smart city kind of environment. So smart city, you need these video feeds from these different cameras that are installed in the public places. If you have to send everything to the data center, to the cloud, etc., that's going to be that's good, but it's not going to be very. So you need some of these to be processed right at the device or very close to the device at the edge. So caching, some of these computation, data analysis, decision making, all of these are going to be made at the device or close to the device as possible. Federated learning is becoming very important, and federated learning on this edge is becoming very important. One of my students basically is working on intelligence. He is working on federated learning on edge computing platforms. So we are talking about ultra low energy consuming machine learning algorithms being executed at the edge. Ultra low energy consuming algorithms being executed at the edge, because edge devices, they have very limited processing capabilities, right? Typical, not necessarily, but typical. So if you are talking about these small IoT devices, for instance, then definitely it's so. So federated learning basically talks about a distributed kind of platform where there is going to be distributed environment where these different algorithms are going to be run, right, in these connected IoT devices. So federated learning, low power machine learning is very important in the context of IoT. Blockchain. We all have been hearing about blockchain. Blockchain is a very good friend. There are a lot of criticisms of blockchain. We ourselves in our SWAN group have worked a lot on blockchain. We have some technologies which are already developed on blockchain, and I'm going to talk about briefly on of these. So blockchain has become very important because blockchain can make a lot of things happen. So we have been talking a lot on security, even the privacy with blockchain. This is something very common. But what about network management? What about this distribution, decentralization with the help of blockchain? Blockchain basically can make many of these dreams come true with the help of its technology. So you are in a blockchain, you are talking about distributed ledgers, distributed everything, distributed ledger, decentralized storage, distributed AI models being executed, right? So all of these, some of these, of course, the achieving these things, some of our students have been working on these things. So let me just quickly talk and very briefly touch upon some of the works, because the time is very limited. Although I promised to complete it within half an hour, but I think I will take a couple of more minutes. So 60 for IoT, right? So these are actually some of these works that I and some of my students in the SWAN group, we have done in the past. One of our very popular works is basically, it was published in the IEEE Transactions on Parallel and Distributed Systems last year, 2020. It is on blockchain at the edge. So basically, we are talking about how you can run blockchain at the edge, right? So, if you are interested, please, either you can write to me, or if you search in the internet, in my Google Scholar profile, you will be able to get a link to it. So blockchain at the edge basically talks about that, how you can run blockchain conceptually at the edge, right? So there are huge challenges, and we have made prototypes, right? And we have demonstrated that it is possible, right? So decentralized management platform for edge device has been considered in our work. And so what we have done is have taken the security of the data, we have considered it and that is generated by the resource constraint IoT devices, how you can secure the data that are generated by the IoT devices with the help of blockchain technology, and protect it at the protect the security at the edge itself, right? So this is one of these works. Another work that some of my students, we have actually a joint project with ABB. So one of the key persons right now from ABB, he is also present in here, Dr. Saha. And so basically, what we have done over there is this work was basically published in the IEEE Infocom workshop last year. So we came up with based framework for for SDNs, right? So in SDN, software defined networks, one of the things that is that is required is basically to have controllers, right? So we are talking about single controllers, then single controllers being expanded and having multiple controllers. Also, people are talking about nowadays. But typically, it's a single controller kind of scenario. Now, these controllers, single controllers become single points of failure. So what we have done is we have come up with a solution by which these single controllers, these single SDN controllers, these single point of failures, if they fail, then how this blockchain technology can help in coming, for recovering this failure. So we came up with a scheme for controller recovery upon failure using the distributed blockchain. So what happens is that metadata that are stored, so these will be used in order to take back the system to a previous state, which was fine with the help of this blockchain. So blockchain ledger basically helps in this particular dream. So in between, I will also talk about a couple of other works I'll mention, but in between, let me just remind you about some of these interesting 60 use cases. I already talked about holographic teleportation. I talked about smart infrastructure, industrial automation, industry 4.0, industry 5.0, industry X.0. Precision agriculture, I and my group, I think more than 10 years, we have been working with different scientists in our country on precision agriculture. We have a number of different solutions on precision agriculture, but it has to evolve because we have already, through our deployment experiences, we have seen that there are a lot of challenges. So anyway, so that is one thing. Autonomous vehicles is another very interesting. Smart transportation, autonomous vehicles are evolving like anything. AI-based vehicle transport autonomy in the vehicles. So these are all happening, right? So these are some of these potential 60 use cases. So I already told about the two different works that we have been doing. Like this, actually, we have number of different solutions which can help in bits and pieces to cater to these kind of dreams of these interesting 60 use cases in future. So we have been working in bits and pieces. We take up a lot of different problems. If you are interested, please feel free to visit my Google Scholar profile and look at my recent publications or the publications in the last 5 to 10 years. You'll be able to get some idea about the kind of work that we do. And if you are interested, we can take, if somebody is interested to collaborate, or, if you need to get more clarity on some of my previous works that have been published, please feel free to get in touch with me. My coordinates are already public. If you just search with my name, you will be able to get my coordinates. So please feel free to, get in touch with me, and we'll be happy to take collaborations further. So I was talking about smart cities earlier. Take the other one, the smart is industry 4.0. We did a lot of work. Our industry 4.0 and industrial IoT course in NPTEL is quite popular, as many of you probably already are aware of. So industry 4.0, we have done a lot of research. We are talking about industry 5, not we, but the world is talking about the next generation, which is the industry 5.0. And people are even talking beyond 5.0 nowadays. So smart factories, intelligent factories, network factories, big data, remote monitoring of machines, machine-to-machine communication, extremely highly reliable networks with high throughput, network supporting high throughput, real-time communications, extremely low delay, low jitter, and high big data rates. These are all basically some key terms that I just mentioned. If you really need to yourself towards industry X.0. So towards this dream, we have been running projects on Industry 4.0, and as I said, with ABB, we are at present running some works, running some projects, and we have done a lot of bits and pieces of different problems we have taken up, and we are. So one of these works basically talks about blockchain-based programmable fog architecture, blockchain-based fog architecture, right? So, and its programmability, right? So I think many of you, I do not need to elaborate, but those of you who are from the network community, probably you are already aware of programmable devices, programmable networks, right? So here we are talking about programmable fog architecture because of the dynamism that comes into picture when we try to realize these dreams that I mentioned, right? So programmability comes as a very handy kind of toolbox for us, and we need to use it to realize some of these different goals. So you see that when you are talking about smart industries, you are talking about edge devices, then fog nodes, then you are talking about, if you are talking about blockchains, etc., deployment of these blockchain frameworks. So you have these different blocks which are going to be, which are going to store the different models and are going to run them. Models means what? Machine learning models, transfer learning models, to be more precise in our work. So these are all going to be executed. So one of my papers, which was published in the TII Transactions on Industrial Informatics in 2020 by Pallab Dev and others, some of my students, basically, this Magnum. Please feel free to look through it. Just in the interest of time, I'm not going to go through it in further detail. But basically, we talk about how we can deploy lightweight blockchain-inspired solutions which can be used in the industrial kind of scenarios. Mentioned earlier about autonomous driving. So one of my students, Chandana Roy, who is already, students means like she has already got her degree. So she did a lot of work on, on intelligent transportation systems, particularly for making, safety of vehicles happen, right? So she came up with the framework which is called the Safety as a Service framework, in short, SAFE as. So SAFE as framework basically was published in the IEEE IoT journal a couple of years back by us. And this framework basically since then have been used a lot in order to make intelligent transportation happen. So here, one of the core components of the safety as a service, system is basically this decision layer. So we are talking about decision virtualization. So we are virtualizing the decisions, right? So decision virtualization is something that we are talking. It's a futuristic thing, but this is basically something that will be useful for autonomous driving and smart transportation scenario. Recently, 2021, Chandana, she came up with the Safe Passe framework for helping in the dynamic handoff in the safe as infrastructure deployment for intelligent transportation. So again, if you are interested and curious, things are already in the public domain. But in case you are not able to find anything, just feel free to get in touch with me. I would be happy to discuss with you further. Smart healthcare is something that I have been working since over a decade now, right? So we did a lot of work. I'm not going to go through it. A lot of important papers, in IEEE Journal of Biomedical and Health Informatics, then on JSAC, several papers in JSAC, Journal of Selected Areas in Communications. Infocom last year, we had on smart healthcare, IoT-based smart healthcare, where we are talking about autonomous over-the-air configuration of IoT devices, right? So this paper got accepted in Infocom. Nidhi Pathak basically worked on it, and so like this, actually, many of my students, they have been working on many of these, and time is very short, so I feel bad that I am not able to elaborate further on these things. So smart healthcare, we did a lot of work. Health Flow is a recent work that was published in the IEEE GlobeCom. So where we are talking about coming up with, so how you can control the network flow, right, of critical data based on the criticality of the patients. So we did a lot of work. Our first work on criticality and controlling flow, basically that work was published in 2009 in JSAC. But this is also a recent work which takes it forward. Another thing is basically this connectivity, massive connectivity. So here, as I told you earlier, that we have done a lot of work on underwater communications. We did a lot of work on aerial communications, and so how you can make these things connected. Last year, we came up with the underwater communication, multimedia transmission, multimedia communication in underwater. Right, it's a huge challenge, as you can understand. Acoustic channel, very low bit rate, and so low throughput. So how you can make underwater these things, your computer vision feeds, right? So camera feeds, how you can send them through underwater channels. So we came up with solutions which we hope that will be used in future. Phantom network is something that we are very proud of. It's a phantom network. You have never heard of this term because we coined this term. It was published in 2020 last year in the IEEE Communications magazine. So this is basically Anandarup Mukherjee. He is presently in Cambridge University as a postdoc. So he basically came up with this technology, and here basically we are talking about something that is invisible, right? So this is something we brainstormed, I and Anandarup, once we were traveling to UK, and at that time the entire stretch of road we brainstormed about how we can see future communications to be, and particularly communications like military communications where stealth technology is very important. So I do not really need to see the drone flying, right? If I want to carry on some operations, military operations. So can we have some kind of invisible kind of communication? So stealth technologies are already in place, but we try to take help of our strength in nano communication technologies. So we came up with this phantom network technology, which was published in IEEE Communications magazine. So it's basically, a phantom network is basically an intangible, on-demand, power-free aerial communication paradigm, right? So where we are talking about how you can make connectivity in places where there is no existing connectivity, where military operations require invisible kind of devices to be in place. So we came up with this technology, and we have compared with nano networks and UAV networks, how they compare. So this is basically it. So like this, actually, a lot of other technologies are there so tactile internet. I do not need to really talk about further. Previous speakers already spoke about it. Digital twin technology. In the we already have a center for manufacturing, advanced manufacturing, where I am also a part in IIT Kharagpur. So we have created digital twins, right? So for digital twins for some kind of manufacturing machinery, along with TCS. So we created this digital twin. So digital twin basically gives you a virtual copy of the real object. So like this, actually, a lot of different interesting futuristic technologies we have been working on. In the interest of time, I'm skipping all of these and to this slide. So this is Sensor Drops Networks. This is a company that I have started, which is incubated in IIT Kharagpur in the Science and Technology Entrepreneurship Park. The URL is sensordropsnetworks.com, and we have a number of product offerings. So if any of you is interested, please visit this website and you can get in touch with me. We have footprints in healthcare, we have footprints in manufacturing, we have footprints in agriculture, and a few other domains, right, in the power sector as well. So we have been working with the CESC for some of our solutions. So thank you so much. So I think I also overshoot the promise that I made at the beginning. So this is basically the team which makes it happen. Many of them, basically, this is a little bit of old picture. Many of them, they are all either faculty somewhere or they are postdocs in some reputed university. But the most important thing is that the credit for all of these goes to this group of energetic students and the past students who make things happen for me and my research group. Thank you so much. So what do you, Deborsi?
Yes. Thank you very much, sir, for this. Yeah, I am audible, right?
Yeah, you are audible.
Okay.
Sorry, by mistake,
Okay.
I muted you. Yeah.
Okay, it's no problem, sir. So thank you very much, sir, for this extremely exciting and elaborative talk on 6G and its various aspects and use cases, applications. So so right now I would like to hand over to Bhingra, sir. Sir, it's over to you for the next.
Yeah. Thanks, Devarshi, and thank you, Professor Sudeep. So now we may have a little break to have a photo session before we start our fourth speaker session. So I would like to request all the speakers and participants to switch on their camera so that we can take a picture.
Thank you. It's a good break time.
So we'll switch off once Chengappa will let us.
Virtual tea could have been arranged.
Nice to see you, Naveen sir, with a new look.
Please turn on your camera. Mr. Khan, or maybe from mobile. So who is saying cheese, please?
IEEE.
Is it done? Not done?
I hope so. And also capture one.
Yes, we are good.
Thank you. Thank you very much.
Thank you, Venkatesh.
So, Alok sir, should we read out some of the questions? Couple of them are there. Should we
I
wait for the question and answer?
I got my part and I have answered. Yeah, I think we should move on to fourth and then let's do at the end. I'll collect some
Okay,
questions.
sure.
Thank you.
Then, in that case, I would again request Deborsi to introduce our last speaker. Thank you.
Thank you, sir. So obviously, last but not the least, we have again one exciting topic is coming out. It's coming up by Professor Devarati ma'am. So she will be talking on terahertz communication for 6G and the emerging applications and channel modeling. So here's a very brief bio of ma'am. So Devarati Sen is currently an associate professor of IIT Kharagpur, India. She was a postdoctoral research fellow with the Chalmers University of Technology, Sweden, and a senior chief engineer with the Samsung Research Bangalore, India, prior to join IIT Kharagpur in 2013. In 2014, Dr. Shen was a visiting faculty with the Institute of Communication Engineering, GUM, Germany. And in 2019, she was an academic visitor with the Department of ECSC, Monash University, Australia. She has about 12 years of R&D experience overall related to the domains of wireless and optical communications, including interdisciplinary computing, mostly on 5G and 6G communications, AI-enabled wireless, millimeter wave and terahertz communication, green communications, large MIMO, cloud RAN, etc. Her research is supported by various government organizations, including MHRD, Ministry of Communication and Information Technology, Ministry of Heavy Industry and Public Enterprises, BEL, HAL, DST, DRDO, SURF, Indian Railways, and external collaborations like Airbus, Samsung, Qualcomm, USA, Ericsson, Sweden, Rosenberg, Techno, China, etc. She has 13 patents published, applied to her credit, including few US patents, and she published more than 100 papers in journals and conferences in review. She is an editorial board member of 2 international journals, recipient of Best Paper Award at Samsung Technology Conference 2010 and IEEE ANTS 2016. Institute of Engineer India Young Engineers Award 2010, IIT NVG Memorial Award 2013, Qualcomm Innovation and Fellowship 2017, Faculty Excellence Award IIT Kharagpur 2020. She is a senior member of IEEE, fellow of Institute of Engineering India and IIT. So thank you very much, ma'am, for accepting our invitation. So it's over to you, ma'am.
Thank you, Devoshi. I hope I am audible to everyone.
Yes, ma'am.
And my screen is visible?
Yes, ma'am, it's been with us.
Okay. After listening a lot of the information since morning, so I will be directly entering into the most promising technology for the 6G, which is the terahertz communications. Applications I will be briefing. Mostly my talk will be towards channel modeling. So terahertz band, if we look into the whole electromagnetic spectrum, it is just beyond the millimeter wave, but before the infrared. That's the gap we are talking about. And this is one of the most promising one apart from this VLC part for this upcoming 6G communications. See, long back when in 2010 we were and the 4G was getting deployed worldwide. So that time the wireless community dreamed of passing 100 Gbps, 100 gigabit per second over the wireless. That was a very exciting talk delivered by one of the professors from Japan in the IEEE ICC conference. And people are very surprised to hear that 100 Gbps transmission over wireless can happen within the next 10 years. His vision was 2020. And today, in 2021, we are seeing and we are thinking that we will be transferring more than 1 Tbps, terabit per second, over wireless. If we are able to do that, we will be really touching the 71% of the total traffic of this whole wireless, and by 2030, it will be really touching the broadband kind of transmission speed. So saying so, I should also mention that once over wireless, we will be touching 1 terabit per second. The broadband connections will have its own level of the higher threshold limit that has to be taken care of. So the speed with which we are moving in terms of the data rate demand for ourselves, and which is driven by definitely a newer applications that are coming up. See, this terahertz band is going to sustain for a pretty long time, only because, not only because it's a very high frequency, that's why it's a very less application is done there, also because of the very wide bandwidth right now available worldwide. So this is the gap in this figure that you are seeing, that the electronics and the photonics, that two different bands are there, and in between the terahertz gap is fitting into. So 100 terahertz to 10 terahertz, this is a first generation target for the current research community to come up with the newer technologies here in terms of all the physical layer transmission technologies along with the access and the higher one to come up with. If we are successful in deploying the network over this range, so the next generation ahead, we will keep on increasing our band. So basically, we will be targeting currently up to a lower range of the terahertz, maybe up to 300 gigahertz, 100 to 300, or maximum up to 500 gigahertz in the current state of the research one. So whenever we ask ourselves why terahertz, so immediately that comes into the point that what are the drawbacks of the current millimeter wave, based on which the current 5G communication research has got matured to a pretty good extent. See, this seamless data transfer, unlimited bandwidth, the microsecond level of latency, as we are putting a lot of the stringent communication parameters on our transmission scheme, like the ultra-fast download also. So we are definitely going ahead whenever the stringent requirements are coming, definitely actually the requirements of the higher and higher bandwidth and other technologies that are coming up. Terahertz is definitely is a promising one to give you a very wide bandwidth. Saying so, I will talk about also the huge amount of the challenges that come in immediately whenever you talk about a very wide bandwidth. So today, whatever your mobile handsets you are operating on with the 4G communication system, all are under the narrowband communications. We struggled a lot in the 5G because like in the history of the communication, first time we traveled from the very low narrowband communication system design to a wideband communication system design. And in terahertz, typically we are going ahead a very wide bandwidth, it's ultra wide bandwidth kind of system design. So in the first range, as we have targeted, that we will be targeting for 10 Gbps kind of the system design. And why 10 Gbps and why we are restricting ourselves to the 10 terahertz kind of communication is only because the non-availability of the physical devices. Wherever our state-of-the-art semiconductor technologies, our optical communication devices, and the integration of the opto-wireless devices are standing today, they're sitting with that technology and the upcoming research. Based on that, we can promise ourselves to go up to the 10 terahertz band because we may manufacture for ourselves the devices for ourselves. And if I go ahead with that, and what is the drawback currently the existing technologies are not able to give us is, say, LTE advanced, and with this aggregation, we have seen 100 megahertz kind of data rate, 60 gigahertz millimeter wave, and even the 77 to 81 gigahertz. That band that are getting now extensively getting used for your automotive radar applications and your pilotless car designs and all those kind, and even actually for your commercial communications, all of them can actually give you with your aggregation and the support of the 7 gigahertz very wide bandwidth around 60 gigahertz can give you an order of 10 Gbps kind of link over a meter. Yes, if you can give a MIMO in link over the 60 gigahertz, your range will be extended. That is definitely there. And also we can go ahead with actually truly 10 gigabit per second over a 7 gigahertz wider bandwidth. But going ahead, what? Going ahead, if I enter into the terahertz next, the biggest problem that will come in front of us is the high path loss. High frequency transmission always brings this high path loss that we have to address. We have already learned about the beamforming technologies, and we are faithful enough on ourselves that we can really go ahead to do something better beyond that. So high path loss, how much high path loss is expected to happen, that we have to quantify first of all to understand whether the existing beamforming technologies will work there or we need to do something better for us. The second important problem in this as a challenge that comes is the compact high power terahertz band transceivers. This high power consumption is expected to happen whenever I go for a very wide bandwidth, because frankly speaking, if I go ahead with a very wide bandwidth, immediately actually all the RF front end, starting from your low noise amplifier to your bandpass filter to your ADC. So if you go by the nightly sampling rate, it goes by the doubling the speed of the sampling rate over which you are transmitting. If your transmission bandwidth is 7 gigahertz, for example, you need an ADC which will be sampling at a 14 giga samples per second minimum. And if you see the data sheet of the ADCs, the current state of the art, you will be surprising seeing the how much amount of the energy is getting consumed only inside the ADC. The heavy power hungry devices are sitting in front of the RF, which gives a very heavy restriction for us to go ahead and straightforward tell that yes, the terahertz system design is going to happen easily as easy extension for the millimeter wave devices. It's not. And our biggest pillar for our success in the millimeter wave was our antenna technology. A remarkable improvement in the research has happened in the antenna technology, which has enabled us to go ahead with the beamforming and adaptive beamforming also. But now we need an efficient ultra broadband antennas to make us enable to go ahead with the terahertz frequencies. So in GIST, we have to come up with a frequency selective path loss factorization. We need a very nice channel modeling. We have to keep on developing the novel modulation technologies, transmission schemes, and as well as the communication protocols. Remember one more thing, terahertz technologies and terahertz communication is getting explored right now worldwide. So FCC has not given us any fixed terahertz band. So currently the spectrum, what will be the efficient spectrum for the first generation or the phase one release is under the consideration worldwide and also under the consideration for the different standard bodies. So this slide tells us about what are the different aspects that we and the challenges that we have to address before we really see the 6G wireless transceivers in practice. So today's talk, I will be mostly going towards the channel modeling and other are, that the physical communication, the network, the device, the test bed and device. and the interdisciplinary scenarios. The interdisciplinary scenarios are talking about application like kind of joint radar and communications, the RADCOM, which is going to be integrated part of the 6G also, as other speakers were also telling. And terahertz sensing and imaging, the localization, the space communication, the nano things, Internet of the nano things, all those, wherever actually you can go towards. So these are the few more cases which will give us the other challenges for the terahertz. So if I see the range of the applications that are coming for terahertz, it is really spread from the nano applications to a macro scale. So these are the typical application parts that I have listed here. You can see that in the macro, it is not only the cellular part, it is the backhauling, it is the front haul plus backhaul as well as the data centers. For the micro cells, you are in the HDTV areas, the seamless transfer of the files for the wireless displays, the access points, the kiosk downloading. For the nanoscale applications, it's the biomedical is upcoming as a very big market for us. And the industrial applications, defense security related parts, and the environment aware communication for the nanoscale implementations are expected to come. So these are some of the applications that I have listed in the upcoming slides. I will quickly go through them. So the next generation small cell heterogeneous networks are going to be operated via terahertz communications. So we are going to tell them that the terahertz WLAN, terahertz WPAN, and this secure terabit wireless communications. So all the terms are going to be changed in the very near future. And if I go in detail about each and every one of them, so apart from the ultra high speed that we are asking for ourselves, starting from the your last mile to the backhaul, we will be also talking not only the seamless interconnections, we'll be also talking for each and every cases, the secured, low powered, enabled, intelligent connection, seamless connection from the end to the back. And I have added here one more that other speakers have also told that, see, the planetary science, the interplanetary communication. I don't say it is a inter-satellite communication. I say it is an interplanetary communication. Today, we are seeing that we will be, we'll generate our communication system. We will be generating our population in Mars, right? So what about the communication from Earth to Mars? So whether actually there is a one-time communication going to be, or there will be a via satellite some communication going to be, via the International Space Station, the communication is going to be. So towards that direction also, the thought process is extending. Interplanetary communication, NASA has a very big drive, even in the ISRO here, for having a very big research group towards this interplanetary communication part. But terahertz communication is the first driving force there, and the key driving force there. Like the other applications in the nanoscale, we understand that the nano transceiver designs, and even in the communication processing code designs and the nano antenna designs, they will be enabling us to come up with actually new nanoscale processors and the nanoscale devices, on-chip devices, ultra-high-speed on-chip devices are expected to come. And Internet of Nano Things, I expect it is an extended version of the Internet of Things, IoTs, that we have already devised for ourselves today. So these are the Tera Wi-Fi, the Tera IoT, Tera space communication. But there is a very nice catch in this Tera space communication and the Tera IAB. This is the infrastructure for the backhaul connections. And that I will be coming with a very new kind of upcoming architecture in the next slide. See, come here and see that the new RIS empowered the terahertz communication links that we are talking about. What is this RIS? This is reconfigurable intelligent surfaces. So today we are really, the way we understand our wireless channel is that we try to go for the channel sounding, we try to take a lot of the measurements, we try to understand our behavior of the channel. We talk about the intelligence about how the device will understand the channel automatically. So all this we are trying to tell that we are trying to say because we don't know, we can't predict. It's a complete random in nature about the channel. If you can predict the channel very nicely, it's very easy for you to devise the algorithms. You can update the algorithms also on the fly. But what about if you can dream of that you can control the channel, you can design the channel, wireless channel, as per your wish. That's where the next generation is coming up. So we are dreaming of a certain kind of the environment scaling up, environment manipulating surrounding us by means of our newly upcoming infrastructures, which will be called as a reconfigurable intelligent surfaces. These are the passive surface, the passive metallic surfaces, which we can go ahead with the programming where we are having some location aware information, we can actually on the fly keep on targeting our beams towards our location. And for that, as it is a passive one, you can understand that lot of the energy efficiency we can really address on the intelligent surface implementation itself. And these are the surfaces that is upcoming one, and you can actually paste it inside your surrounding you wherever you wish to deploy your network. Hence, it has its application starting from the satellite communication to your terrestrial communication to anywhere, even actually in the UAV networks. You can manage your network to such, you manage your environment in such a way you can wish to design the improve your QoS or you can improve your QoE. A very big, this RIS enabled communication system is going to be a actually integral part of the upcoming 6G standard, at least from the TSDSI part, which we are going ahead from the industry side, from India side, India's industrial area. So terahertz is also going to be a very big actually implementation for the medical world. I am not going in deep towards that. If I proceed towards the cellular communication and the wireless communication, commercial communication part, so these are the few areas where the research extensive is required to be done. See, terahertz with ultra-massive MIMO people were talking about, I should say it is not an ultra-massive only, it is a cell-free MIMO. We talk about not only the cell-free network, it is a cell-free massive, ultra-massive MIMO, where you can think of a virtual antenna arrays, the huge virtual antenna arrays, which are spatially different from each other. They can construct a huge virtual antenna array structure where the individual devices need not to have a massive MIMO structure on it, but as a whole, in a coherent fashion, inside a network, inside a particular environment, with the help of intercognizance of all the devices, you can structure a artificial huge structure, which is a self-free massive MIMO structure. Tomorrow's network, tomorrow's self-free massive structure will be something like this. Suppose you are traveling with a ultra high speed train, bullet train at a speed of 100 km/h. It's not possible for giving you support via the standard and the fixed base stations. So the last mile connections cannot be happening with a single fixed base stations to you. It should happen with a cluster of the base stations, and that cluster of the base station should keep on following as per the direction of your movement. So what I'm saying is each and every user specific cluster of the network, cluster of the base stations will be associated to. So today you are selecting your own base station. For example, 5G is telling you will be selecting your own network. But what I'm saying is tomorrow user will be selecting the cluster of the base stations from a network or a combination of the networks, and that will completely giving him the access according to his demand, according to his movement. So mobility enabled dynamic selection of the network is expected to happen if you really wish to reduce the latency at the last mile. Terahertz enables this implementation of the self-free massive, ultra-massive structure of those MIMOs. And others are definitely, it's a purpose of all this, the 3D beamforming and this urban environments, automotive applications, the security enabled. We have already talked a lot about all this. And see, actually the vehicular communication, the infrastructure one and all others are already being discussed, so I'm not entering there. So why terahertz and all others, that this slide also is partially being discussed about some of my previous speakers. So we find that actually compared to the visible light, currently terahertz is leading the research in order to touch our dream of 1 terabit per second connections, going ahead with that. But how to extend the range, because terahertz will be giving a huge path loss, as I have told. That actually is a challenge right now for us also. Now, quickly coming to the measurement campaign. So, terahertz path loss, if we wish to see, and who are the killing stuff for us, if we wish to understand. See, in the millimeter wave, it was the oxygen particle which killed our gain in the channel, and we were really struggling to find out where to move. Especially 60 gigahertz oxygen absorption was terribly high. That's why for the automotive radar applications, we have shifted to a 77 to 81. Come to the terahertz, oxygen is not that much killing, but water molecules, they are the main killing stuff, and their absorption is really very, very high. So non-line of sight path, another point I will come here. See, millimeter wave, mostly the communication will be dependent upon the reflection, the phenomena called reflection from the multiple objects that you find in the environment. And reflection may be first order reflection, maybe second or third order. The ground reflection also we have taken care of. And if you can capture from your energy from the channel, from the multiple reflecting paths, it may be from the clustered multipaths or it may be from the individual multipaths. But reflection is the major phenomena that will help us to deploy our 5G communication system. Come to the terahertz, the biggest problem of ours is the scattering effect and the diffraction effect is dominating over your reflection. Lot of the measurement campaigns which are reported, they are saying that majority cases, scattering is dominating over our reflection. And our biggest problem is how will you capture the scattered energy into a receiver, because scattering effect does not happen to a particular direction. Reflection can happen to a particular direction. Scattering is almost all over your area in a 3D space, I should say. So it was important for us to calculate how much is the gap between the scattered wave, how much loss is extra happening because of scattering and the diffraction compared to our reflection. If I don't consider the scattering and the diffraction effect, you will wrongly calculate that we have a 12.2 dB high actually channel power, receive signal power in the receiver front end. And if you go ahead with this kind of design, neglecting the scattering and diffraction effect from the channel, your link budget is not going to work once you deploy such system in practice. So going ahead, the channel measurement campaign also have dictated us what are the typical frequency domain where actually what kind of applications we can go ahead with. Uniformly, you cannot go ahead with actually the whole band, 100 to 300 gigahertz, whole band flat spectrum, it cannot be utilized for any typical kind of applications. For example, here the blue circles that you are seeing, 120, 183, 325, 380, they can be utilized for the short duration, very close communication, maybe for the micro and the nano cells. But for the macro applications, you have to shift your spectrum to some other cases where the green circles we are showing, the attenuations where actually will be even more lower so that we can travel the higher kilometers. So broadband and mobile and fixed application cases, the 77, 140 gigahertz and 240 gigahertz, these are the gap, these are the spectrum holes where we can think of for our long distance communication setup. So other different frequency bands, if I go ahead with, then we will be seeing that compared to your millimeter wave and the terahertz bands, some cases we are even actually seeing that compared to your sub 6 gigahertz bands, the additional losses that are coming that are close to the 10 dB per kilometer cases if we are moving towards the 300 gigahertz band. So the extra design, the extra effort that you have to come up with from the signal processing side or from the modulation side or from the waveform side is that currently it is that this 10 dB per kilometer wise, if you wish to move up to the 10 kilometer kind of the system design, so at 300 gigahertz, next after 140 gigahertz definitely, Beyond 140, the 300 gigahertz is another good area where some long distance transmission we can dream of. So if I go for ahead from here, and if I try to see that what are the different frequency ranges now we are getting, what is the bandwidth we can really get out of this path loss, if I go ahead with the path loss kind of a study, and then we will be seeing that these are the frequency ranges up to 910 gigahertz I have listed here. The contiguous bandwidth that we can go up to 130 gigahertz. So compared to your 7 gigahertz, that's 60 gigahertz bandwidth, at 60 gigahertz transmission frequency in millimeter wave, your 275 to 320 gigahertz itself is capable to give you a 45 gigahertz contiguous bandwidth. It's now up to us. How we will design our systems, how can we utilize this 45 gigahertz bandwidth at a stretch? And I believe that one day in future we will be able to utilize this, but today's signal processing and today's devices are not capable to really capture the signal over a wide 45 gigahertz wide bandwidth. But definitely, actually, 2 gigahertz wide channels and the consecutive 6 channels, if we are thinking of, so over a 12 gigahertz first layer, phase 1, 12 gigahertz wide system design is the target currently going ahead. These are some of the measurement campaigns that people have done, and a lot of them have also designed, and they're capable to capture the channel over a 4 gigahertz wide bandwidth. We are dreaming of actually 12 gigahertz by concatenating or aggregating it at the receiver end, but at a stretch 4 gigahertz channel capturing and its behavior we could see. These are some of the path losses and the comparison about how actually it is going ahead compared to your 28 to 73 to 140 gigahertz. What is the extra losses in the terms you are going to get? And you are seeing that 5.7 to 10 dB, as I have already told, the huge losses are expected to happen. So compared to your free space path loss, because the free space path loss portion is so important, because I was talking about the interplanetary communications and also for your inter-satellite communications at the low orbit cases, you need to really characterize how much amount of the dB losses we are expected to happen if it is at the 140 gigahertz transmission going ahead there. So on the terrestrial to the non-terrestrial to the deep space communication part, so the different amount of these path losses we have tried to characterize and capture. So now the gain, if it is the water vapor molecules that we understand there, so what is the loss in the gain that is expected to happen? 60 compared, this slide we have tried to compare between 60 as well and the 0.3 terahertz only. So the path gains expected to be down by the 10 dB once again. If you are traveling over the large array part, and which again gives us another level of indication that is not only the path loss, it's also because of the scattering, this huge down of the path gain is expected to happen. So scattering diffraction losses, once I am talking about and how this measurement is done, under what condition this 10 dB losses we could find, if you ask me, the other conditions were something like this. So number of the multipaths that has been observed at this 0.3 terahertz was only 5, and 256 or 256 ultramassive MIMO system was enabled to find out this kind of the losses that are expected to happen in the terahertz. I would like to mention here another experiment that has been conducted, the outdoor cases. And there actually the building materials and the different transmitter receiver heights that are maintained to be 30 to 1.5, and with the mobility of the receivers as is shown here. This is a Manhattan city, and these are all the buildings, and the receivers, movement of the receiver is happening in this fashion, and how many really multipaths you are going to get, and the outdoor itself, if you try to go ahead with, and with a distance of 160 meters, if I go ahead with, and this ultramassive structure of 256 cross 256, how this receiver signal strength, RSSI value, receive signal strength value we are measuring, and their different type of the outputs with respect to the reflected versus the scattering power expected to happen. This typical table tells us that if the incident angle on a particular surface is varying from 0 to 90 degree, and depending on the, remember you are in terahertz, so the zooming capacity of your electromagnetic wave has increased tremendously. And so the smoothness that we see here today and the smoothness that at terahertz you will see, there is a huge difference also. So the smooth, intermediate and the rough surface, the intermediate and the rough surface, which will be in the terahertz looking as a rough, it is exactly a very smooth surface in millimeter wave. That's the difference I'm saying. So in the millimeter wave, we could not see at all any such kind of the scattering whenever our incident angle changed from 0 to 90 degree. Mostly the reflection, otherwise no absorption, huge absorption has taken place. But here you see, as our incident angle is keep on changing, some of the cases the scattering power is becoming more from our reflection power that I was saying. And if we cannot improvise, the technique of capturing the scattering power from our environment in the receiver front end, then actually the huge losses are expected to happen. It will be very hard for us to go ahead with the baseband algorithm designs inside the receiver. This is a link budget analysis. I tried to keep it to give us a glimpse of an idea with the existing modulation schemes like a 256 QAM cases, where our link budget is. A budget is something like which will always tell you if you go release your electromagnetic waves with a particular power, and if you have a particular distance to cover at the receiver front end, are you ending up with some amount of the SNR, the signal to noise budget left with your hand, so that you can think that the link establishment can happen. So this we varied from 30 meter to 70 meter to 100 meter in an outdoor situation, where we thought that the transmit power will be really very less, like minus 5 dBm kind of transmission we targeted, because remember terahertz communication is expected to happen with a very, very energy efficient fashion. At 140 gigahertz, if we proceed and if we don't go ahead with our any antenna gains, we will be ending up with a very low received signal power of minus 91 dB kind of. So it is almost you are having nothing left and you cannot recover your signal at the very front end of the receiver. If I go ahead with a 51 dBi kind of transmit plus the receive antenna gains, and we will be ending up with a 8 dB, and it's possible to go ahead with a up to 100 meter distance with a little bit improvement has to be done for the antenna side. And this whole calculation was done with a 256 QAM kind of transmission of a modulation scheme and 2 gigahertz wide bandwidth. Remember, we can reach really up to a 96 gigabit per second, which is very close to 1 terabit kind of application data rate that the terahertz communication can promise if we concatenate the 6 channels that I was talking about. Consecutive 6 channels, if we aggregate, we can really go ahead up to 96 Gbps and up to 100 meters is possible. You may ask actually where from this 51 dBi gain will come. Remember, as you are in a terahertz, your wavelength has got really down, and so dense packing of the antennas we are expecting to happen, and with the improvement of the antenna technology, definitely 51 dBi is not a very big promise kind of. Closer coming to the channel taxonomy and the way the channel modeling currently is going ahead. What should be the approach for doing the channel modeling for such kind of communication system? See what you are having here. You have a non-line of sight propagation where you have refraction, scattering, reflection, and multipath. All are coming into picture. And dominating factors will be scattering and the reflections, both of them, as well as the diffraction there. You have a small scale mobility where the micro Doppler effects are expected to come. You have the spreading loss as well as the absorption loss also. And if I talk about the way people are doing the terahertz channel modeling, you have to keep in your mind that you have the, based on the scenarios, you have the either indoor, outdoor, or the nano scale. So you have the application starting from macro to micro to nano. So the channel will be widely different for all these three. You have to have a deterministic model or some stochastic model, or you may have a hybrid approach. So I will show in the next slides whether we can go ahead at all with the deterministic or whether go ahead at all with the stochastic, or we need to go ahead with the hybrid modeling approaches. And definitely you have the applications like with the CISO as well as the MISO. Deterministic channel modeling, what does it do? It actually based on the electromagnetic wave theory, and it accurately try to model the channel. But what are the open problems and the challenges there is, your channel itself will be, with a lot of the material properties that are having, and we are dreaming of actually modifying our own channel by means of the implementation of these intelligent reflecting surfaces. So the material property will be broadly actually dominating your channel modeling aspect. And every material will have is different kind of the behavior from your 1 to 10 terahertz kind of the wider range. And their geometrical plus the optical property, both you have to consider. And developing some efficient 3D kind of a your ray tracing simulators, that itself is a very, very challenging and very big task going to happen, because your channel is going to a very wide band channel. Ray tracing for a very, very ultra wideband channel itself is a very fundamental problem by itself. And this time varying properties, how will you tackle this time varying property of this channel right now? Because you are targeting an application where the pedestrian speed 2000 kilometers per hour, the vehicular speed you are trying to track it at a stretch. Remember one more thing, actually, this very wide band millimeter wave channel model, if you go ahead in a 3GPP channel model, whatever is available online, you will see that the channel model has not covered beyond 80 megahertz. They could not even have any kind of the channel sounding there. And that's why there's a major drawback there. They could not actually implement the RIS because IRIS concept itself was not there. They could not actually go ahead with this vehicular speed of 1000 kilometers per hour kind of. They don't know what is going to happen. Because of the very wide bandwidth, two more very important effects are expected to be visualized here that I will tell a little bit later. Dual widebanding effect that is expected to come, which we have never seen in the millimeter wave. Higher range of the millimeter wave, people have reported 1 or 2 places, but people have ignored it because that was not that much required and that much actually important for us to understand our channel modeling millimeter wave. So these are the very basic kind of differentiation that we will look into. So deterministic channel model does not sound to be very promising approach for your channel modeling. So next is the statistical one, what we have done also for our 4G cases and millimeter wave. Statistical channel modeling try to go ahead with the statistically try to model the propagation characteristics based on some empirical channel measurements, try to fit that measurements with some kind of the distribution. We call that our channel is Rayleigh distributed, Rayleigh distributed, Nagakami distributed. Our log normal distribution is there for our large scale fading. Basically, all those distribution which we get because we do extensive channel measurements and then we try to fit it with some known distributions. But what if the situation, if it does not fit at all with any one of them, because you're very wide band wise, the behavior of the electromagnetic waves is continuously changing. So you cannot go ahead with a fixed kind of the distribution over a simple 12 gigahertz wide channel at a terahertz frequency transmission. Another important thing is the statistical distribution also helped us earlier to model the multipath parameters, like how will be the distribution of angle of arrival, angle of departure, the time of arrival, all those complex amplitudes of all those. So we have learned from the millimeter wave, if we wish to go ahead with the beamforming, we are not only talking about the time frequency, we are talking about the spatial domain. We are talking about the space-wise, the freedom, because antenna gives us that domain freedom. If you wish to give actually a beamforming, you have to have a priori knowledge about the probabilistic nature of this direction of arrival and direction of the departure. Otherwise, you cannot go ahead with the beamforming. Transmit beamforming, neither transmit beamforming nor the receive beamforming. So we trusted a lot on the statistical channel modeling for our millimeter wave. Now, come here. So what are the open challenges for the terahertz? The statistical modeling of the temporal broadening effects that we will be seeing here, the frequency selectivity that will lead to the huge distortion of the pulse shaping for the temporal broadening that is expected to happen. And that will, it can actually broaden the duration of the pulse, actually the dozens of the times that you will be seeing here. And that cannot be neglected here in the terahertz cases. How to model it in the statistical fashion is a big challenge. On the top of it, we have seen the cluster behavior, yes, in the millimeter wave also. But here, because of this very fine wavelength that we are talking about, and very high frequency and very fine wavelength, basically, overlapping clusters, the amount of overlapping clusters that we will be visualizing in terahertz will be enormous corresponding to your millimeter wave. You may ask actually whether the sparsity is going to be more or not. Definitely your sparsity is going to be more. But remember, actually the behavior of all the materials have got also changed. So earlier, actually, the wavelength gap above which you have seen the clusters, now you will be able to zoom in more. So the overlapping cluster effect is expected to be viewed more. So this cluster modeling itself is required to be looking into in a different fashion. On the top of that, see, there is a spatial modeling also. And see, most of the cases, the measurement campaigns are reporting that the temporal as well as the spatial, that modeling should not be looked into in a different way. Should be looked into the as a joint modeling. Temporal and spatial joint modeling is expected to be done for our terahertz. If you try to go ahead with a different one, and your signal processing design will be completely going to the wrong direction. So what? So finally, actually, people have also tried to explore the hybrid channel modeling part. We understood that the ray tracing is having its own kind of the advantages. And also your statistical modeling is having a very good actually modeling aspect in order to design our signal processing algorithms, because that's a statistics based. But geometry-based stochastic channel models, or the GSCMs, which actually gets the benefit of both the statistical, the ray tracing based one, as well as also the statistical one, combined one. That approach actually now people have realized that will be the good way to proceed. Even for the higher range of the millimeter wave, close to 100 gigahertz also, that it is now actually well understood that the hybrid channel modeling mode will be the best way to proceed with. What are the open challenges if we try to go ahead there? So statistical and RT, this is, we call it the SRH approach. So they are having a very high efficiency but lacks a lot of the accuracy kind of the part. There is a question on the accuracy part, definitely, though the efficiency will be high one. This the dominant rays like the line of sights and the reflected, that will be determining the RT techniques. How will you get the dominating rays all the cases in terahertz? Because since beginning I am continuously telling, some cases the scattering phenomena can dominate over your reflection. So you have to be very careful. If you trust on the only RT, especially for the line of sight cases and the first order reflection based modeling, if you at all try to progress, you will be miserably failing for such situations where the scattering will dominate. But there are several benefits also. For example, the accuracy wise, it will be definitely going high. Complexity wise also, very rich multipath effects if you consider such certain cases where the multiple rich multipaths are expected to happen. So using the statistical modeling, some low complexity model, you can really go ahead with. So there are actually several deterministic versus statistical versus hybrid applications. So accuracy, computation complexity, applicability, and your geometric information material property requirement wise, if I try to classify how the progress should happen for the terahertz channel modeling. So it is a huge area. So I can simply say the wideness, the range we have seen for our millimeter wave. Currently, if you open the 3GPP channel model document, so you will be really see the vastness that we have tried to capture in the 5G channel model itself. Terahertz is going to be even wider than that, and the depth wise also and complexity wise also, it is expected to be even certain range, several hundreds of the times more complex and more wide and more deep. We are expected to keep on opening the applications like the full duplex kind of transmission. We are expected to happen. We are expected to happen that the applications, the other cases that we have seen, that it is a contiguous air space to air to ground to the deep space going to be. So every situation wise, if the terahertz is expected to come, so they need to be, some cases they need to be integrated fashion, the modeling should happen. Some cases they should be separated out. But as a whole, I should say the promising approach should be the geometry-based stochastic channel modeling. Apart, it is one step ahead of your SRH. And where actually the scatterers are placed over the Euclidean plane with the probabilistic fashion, we understand. The impulse responses are evaluated partially by the rate tracing techniques wherever possible. Later cases, no. The time variation property of the channel impulse should be captured. The instantaneous channel impulse response that should be determined by the surrounding scatterers, and you can progress, go ahead with. The balance definitely should be there, a trade-off between the accuracy and the complexity. Because lot of the cases that channel modeling we have done in for our millimeter wave also, because it is the complexity because of which we could not make it so much attractive in the lot of the cases. So we have trusted upon the statistical one, which was mainly the driven by the practical experiments. We went back and tried to fit with the known distributions kind of. But as terahertz is so unique compared to your millimeter wave, so that philosophy is not going to work with us. So we have to come up with a trade-off between an accuracy complexity in between, a model which will give a very nice balance between these two. And this GBSCM is a good approach to start with. I'm not saying that this is the only way and this is the last way that we all, the community, the channel modeling community, is going to converge. But we see and we feel that it is a good way to start with a lot of progress. And GBSCM actually can capture the two different types of, it's a regular as well as the irregular one. I'm not going in detail about all this. If anybody is interested, we can go ahead with that. The last slide it is, and it's a very important phenomena that I wish to share with you. See, actually, we have learned, we have understood that the channel should be looked into time. It should be looked into the frequency. So time, frequency, space, and also in the Doppler domain, we are talking about a very high speed that terahertz 6G communication is expected to encompass. So channel now has the 4 dimensions. It is not at all a 2-dimension for you in our future. If I try to see how I can look into the channel, I can look into the channel in the spatial and the delay domain. I can look into the channel from angular and frequency domain. I can look into the channel in the angular delay domain also. So this spatial frequency channel to this angular delay channel, you can go from one to the next via our 2D IDFFT or FF2D FFTFT points. From spatial to angle and frequency to delay also, the very nice relations are there. And our friend IFFT is also there. From the frequency domain transformations, you can go ahead. That's true. But actually, the system designs, if you try to see, you have a huge flexibility now in your hand in the receiver design. The way you are looking into the channel will guide you to design your receiver. It is not required to design a receiver which will always look the channel from the spatial delay domain. You can make the receiver design so flexible. If your receiver understands the channel, if it has the capability to look into the channel, one time through a spatial delay domain, next to the angular frequency domain, to the next angular delay domain. So I am not saying that I will always look into the channel through a one window kind of. What I will look into? If I look into my channel into a spatial delay domain, I will see a very nice effect called the delay squinting. If I look my channel into the angular frequency, I will look a very nice phenomena called the beam squinting. If I look, what does it mean? So delay squinting means that the different multipaths that you are over the different frequency wave, if you are trying to see the different multipath components, they are seeing actually the different kind of the delays you are going to look into at the receiver part. Like that, actually, the different if I am having a multi-carrier communication scheme, So over the different subcarriers, I will see the different angle of arrival. So the beams that are arriving over the multiple subcarriers, you will be able to see that there are the different in the angular domain. There is a difference in the angle of arrivals over there. So that we are calling as the beam screen. So how I will design my receiver algorithm is over a waveform modulation, over a waveform symbol from the carrier number 1 to carrier number 1024 or carrier number 2048. I see that the different way the angle of arrival is happening. So the beam has this is called the squinting one. So you need to be very, very careful about when you are designing your algorithm. So algorithm really cannot be designed one time and can be dumped on your FPGA boards or dumped on your FiMac your processors and FiMac module. So it has to be adaptive the way you are looking into the channel. That's the main message that I wish to give you here. And the last one is actually the angular delay domain. If you go there, you will see there's square diffusion effect also. Application of it and how I will implement the effect of this square diffusion in our signal crossing cases. And definitely actually for multiple situations like your advanced threaded informing cases, all these issues of your delay squint, the beam squint, and the square diffusion effects that are expected to be addressed there. I would like to end here. If there is any question, I would love to address all of them. Thank you.
Thank you very much, ma'am, for such a interesting and lovely walkthrough of terahertz communication and its applications in 6G and other thing, and also precisely mentioning the areas of challenges and probable solutions that can be done, and also some futuristic aspect. So so obviously before I hand over to Chengappa sir, I would like to thank all the speakers who joined us today for their valuable time, and it was a really wonderful session with lots of knowledge and information on 6G. So I hope this will be helpful for all the participants. So now it's over to Chengappa sir for like Q&A session and conclude this session today. Thank you.
Yeah, thank you, Debraj. I see Dr. Dilip sir has a question to Debrati ma'am. So Dilip sir, would you like to unmute yourself and ask the question to ma'am? So that we keep this session interactive.
Yeah, hi, Professor. So one question is on where should we use terahertz communication? Indoor versus outer space? Like we've seen holographic communications in Star Trek, like episodes and stuff like that. And, you know, maybe indoor communications also, maybe data comes on wired and then you have a holographic interaction wirelessly. So should we focus primarily on indoor short-range wireless, you know, high bandwidth communications with terahertz, assuming, you know, reflections and scattering are happening on smooth surfaces? And for outdoor, you know, maybe it's for downtown deployments where you have a lot of building walls, but they're smooth, and so, you know, they can help with that reflection scattering problem and gathering the signal. And then, yeah, if you can comment on Star Trek, like outer space applications. And then one last question is about heat. You know, 100 terahertz to 200 to 400 kind of terahertz infrared starts to hurt our skin. Has anybody studied any impact of 10 terahertz? Maybe that's okay.
Yeah, thank you. The first question was actually the application wise, whether the research should be fast in the indoor or the outdoor. Currently, actually, the research is going on parallelly both the indoor and outdoor. Believe me, the interest is more on the outdoor. Industry is looking for the outdoor cases mostly. Standardization activity is also moving towards the deployment for the outdoor. Why? Because two are the driving forces. Number one is we have the devices which can handle 2 gigahertz wide spectrum. And thanks to the aggregation that we have learned long back, so we can aggregate and we can increase the bandwidth that I was saying up to 12 So it will help us to go a very large distance. And second important thing is whether actually we have the antenna or not. So antenna technology, with the current technologies of the antenna and the wavelength as it is really going slow and slower, low and low and low. So lambda by 2 is really helping us to go ahead with a very dense packing of the antenna arrays. So already I hope you know that people have demonstrated 2048 cross 2048 antenna structure. So with all these three combining, I'm saying that people have already demonstrated the outdoor communication link with horn antenna at 140 gigahertz with 256 WAM. People have already received the transmission. It is true that it's with horn antenna, so a lot of the alert travels are there. It is not a very wide range, but it is at outdoor. So by inspired with this very recent experiment done, so we are really very hopeful that with the agreement of the other improvising, the other sophisticated understanding of this channel modeling and the signal processing coming up, very near future outdoor terahertz communication will first come for deployment, parallel to indoor. That's one. The second thing is actually terahertz for your deep space communication. You go ahead and look into this Mars rover, that's mission from NASA. You go ahead with ISRO's Mars mission, the MOM mission. Terahertz antenna has gone to such an excellent research area for them. And see the way they have implemented the communication system, what exactly the communication system they have done there. It is fully terahertz, and not today, long back they have done it. So now what am I saying is, now the interplanetary communication may not be directly from Earth to Mars, but maybe at least from the Earth to the International Space Station and then International Space Station to the Mars. Why not to dream about that? Okay, so interplanetary communication also, if you go to the NASA's website and try type there the interplanetary communication, you will see the funding that is currently going on there, and their first fundamental base is the terahertz communication. If you ask me where are we standing in India, so terahertz antennas, terahertz RF front-end devices, they are getting actually tested, manufactured and tested in some of our very finest laboratories like Samir Calcutta, Samir Bombay section, as well as our SAC Ahmedabad laboratories. So we are manufacturing our terahertz devices and it is getting tested in India. So worldwide, you understand, Japan has long back, they have given us how transistor will be designed and will be expected to work in the terahertz zone. They have done it in the year of 2013-14 only. Only problem is that they don't publish it in the IEEE forum. But once you listen them in some of the good conferences like ICC Globcom, you will see where the device way Japan, Taiwan is standing right now. Even Korea. I hope Dr. They will agree with me. They are in the device side, actually, the huge research is going on in that direction.
Thank you, ma'am. So there is one more question from Connection sir to Devrati ma'am.
Chengappa, one more question on heat. 10 terahertz.
Sorry, sir. Yeah. So I think, I think there was a third dimension to your question.
You'll always be worried about is it going to burn the skin?
Yes. So when 60 gigahertz communication was getting talked about, it was the year of 2007-8. And so the same question was asked to Professor Repaport openly, that what will happen over the human, what is the effect on the human body? 60 gigahertz, today 60, not only 60, 77 to 81 gigahertz is in practice for your automotive radar and your next generation Volvo car, electric cars, everything will be enabled with all of them. So I should not say that people are not objecting. I should not say that people are not actually doing the experiment and trying to see. But another way, if you open the medical journals, you will see that people are talking about the terahertz based instrumentation, where for the arthritis cases, they can actually heal some of the organs and their tissues as well as the bones by injecting the terahertz rays inside the human body. So, how are you using it? What purpose you are using it? How you are controlling all of them? And how they are also using it for the imaging purposes. So medical journals are far ahead than our communication cases, like right now related to your terahertz communication. It is getting used already. So some people are against it, some people are already using it. So I wish to put the comment here itself. Does it answer your question?
Thank you, ma'am. Thank you.
Okay.
Thank you, ma'am. So one more question for you from Ganeshan sir. Says, what is typical phase noise expected at 140 gigahertz LO?
Yeah, and very nice question. Apart from when I was talking about the front-end RF devices, so I missed out this phase noise related portion only because actually that non-linearity, not only the phase noise, non-linearity and the phase noise, these are the other two very important pillars that we have to address. Phase noises are extensively going to be high there, as we have understood also in the 60 gigahertz and above. But my question is actually, but my approach will be to address this RF components, design of the RF components, and how will we address these phase noises in the signal processing part. The knowledge that we have gathered for the millimeter wave is not going to work there. Only because actually this phase noise driven the distortions that are expected to happen at terahertz is much more wider compared to your millimeter wave segment 7 gigahertz wide bandwidth, though we have not used this whole 7 gigahertz there. Yes, we have to address it. People are talking about a different thing. People are talking, why not the antenna technology? The antenna guys, they address the antenna design such that it will be compensating the non-linearity of those power amplifiers and also the phase noise effects that are expected to come. Why not the next generation antenna will be aware of these distortions and will compensate it inside the design itself? That's a very new approach that are coming up. But also from all other parts, means the signal processing guys like us, we are also trying to devise our new detector designs, nonlinear detector and nonlinear signal processing, and which will be also compensating the phase noises and the nonlinearities that are coming from the front end parts. That research is also going on, knowing that the state-of-the-art devices are having such kind of the restrictions. But next generation research is also looking ahead in a different fashion towards the antenna technology.
Thank you, ma'am. We have next question to Dr. Sudeep Mishra from Shobha ma'am. It says that what are the privacy and security issues of wearables in healthcare, and how will it be different in 6G?
Yeah, so thank you. Important question. As I said during the talk also, that privacy and security issues are very important with IoT and IoT adoption in particular. So basically, so we can come up with all these kind of different attractive technologies like these wristbands and smart wearables, etc. But ultimately, we are also concerned that so what happens to the data that is taken out from our from our physiological system. So this is very much of a concern. So all I know is that a lot of work has been done so far in the context of healthcare, particularly data privacy and security. Even for IoT and wearables also, so a lot of research has been done. What I do not know is exactly how 6G is looking into this privacy and security issues. So for wearables, and whether there is any specific focus in 6G on this. I think there are other speakers who might have knowledge about this particular 6G, but so in terms of whether it is 6G or not, so what we need to understand is the concern is something that is irrespective of 6G communication. So so privacy issues are very important. So 6G communication basically, so whether it is going to come up with any specific kind of because the issues are not going to change, right? So all that is going to change is basically how you approach the solutions. So so what are the new solutions that are going to be there, etc. So I do not know for sure that whether there are any specific focus on privacy and security for wearables from a 6G viewpoint. But yes, that lot of research is being carried on IoT, healthcare, privacy, security, and particularly with respect to wearables.
Thank you, sir. Probably a follow-up question, and you can extend the answer on the same. So the next question goes like, how do you think the emerging 6G technologies such as network virtual reality and holograms would improve, I think probably that would be remote healthcare, and could there be any potential applications to deal with contagious diseases and pandemics?
Yeah. So I saw this question being asked by Dr. Varun Saha. So so thank you for the question. Let me tell you that so as all of us we spoke about that so holographic teleportation, etc. These are all coming, right? So although we have been seeing in the sci-fi movies, but this is something that probably is going to happen in not so distant future. So one thing that is going to definitely so it is once it is there. One thing that will be useful is particularly for infectious diseases like the current one. So already we have seen that it's a huge risk for the medical professionals to come close to the patients, right? So with this kind of holographic technology, what will be possible is that virtually the patient or the doctor, they can come, patient and the doctor, they can come close to each other. And you really do not need to probably you do not need to worry too much about the infections, etc. In that kind of technology. Why I say probably is because so in holographic technology also there is some kind, I do not have any clear understanding because I do not work in that area, but people say that there is talking about so mass transfer and all of these, right? So again, so in these kind of nano kind of things, whether this corona is going to be binding to these nanoparticles, and if you are bringing it close to the doctor, so how the risk can be avoided, I do not know. But it's a very interesting question, and I appreciate this thought because it is something that probably can can transform the medical world to a newer level.
Yeah, thank you, sir. Probably one last question for you, and then we can go to the other speakers. So it says, what is the major challenge you envision in edge computing being implemented for 6G? Will the user equipments be efficient to handle complex and large computations continuously?
Is this a question to me?
Yes.
Yeah, okay. So mobile edge computing and edge computing in general, right? So this is basically all. So basically, so the whole thing is that this vision is very important and attractive, right? So you do not need to really throw all the things out to the cloud, it's fog, etc. So for further processing, you need to do some of it at the edge itself. So edge computing, is interesting, required because you need to cut down on the latency drastically. Not only latency, overall network performance also will improve. But you need to really take help of other computing technologies, right? So not just communication is going to help. You need to take help of other computing technologies like machine learning, etc. So for example, one of my students in the paper in TII that I presented, what he did is that for mobile edge computing, what he did is he took help of transfer learning models being so implemented, being deployed at the edge devices, right? So you have already pre-trained models, and they are going to be deployed at the edge devices, right? So to some extent, these kind of things are going to help. We also tried doing it for our work on network of drones a couple of years back. We tried to do the same thing because our Raspberry Pi on the drone it cannot really do all the processing over there, right? So we use some pre-trained models, etc. So that also comes at a it's not a very, I will tell you that there is no easy solution to these, right? So there are a lot of technical challenges that are involved, so you try to improve it a bit, but you still do not have a complete solution, right? So why mobile edge computing or edge computing in general has become very interesting is because of so you have the problem, you need to be there, but at the same time, so you do not, you have a lot of research challenges which will have to be addressed, right? And that is why it is so interesting, and so many researchers around the globe are working on it.
Yeah, thank you, sir. So we have next question to Dr. Saptarishi. From Ganapriya ma'am, it goes like, in 6G, we are looking at AI-enabled intelligent networks in varied dimensions. Is blockchain technology getting embedded in 6G specs itself or at the app layer?
Is the blockchain getting
embedded in the 6G specs itself?
So maybe like I'll
sorry,
rephrase. I'll rephrase. Thanks.
Sure, ma'am.
So what we have seen in 5G, right? Like considering the data analytics and AI, it started with the network data analytics function getting introduced in 5G, right? And 6G, we are looking at AI getting embedded in every layer of the 6G network. So similarly, I wanted to understand, because we are talking about blockchain at varied scenarios, even in today's presentation. So wanted to see if this technology is getting embedded as part of the 6G specifications itself, or are we still considering more at an applications level solutions, or it can be enhancing the operations efficiency, so we are leveraging blockchain technology. So I just wanted to understand if how is this technology leveraged? Is it like getting embedded into the 6G specifications itself, or it is more at the application layer?
I just given one analogy, ma'am. Actually, the way we started trying to embed the virtualization into 5G, that will be leading to the analogy of your blockchain. See, virtualization aspect of it is a platform type of environment actually. But in the 4G days, we started thinking that do we want to move out from a dedicated to a virtualized platform? So when the standard of 5G started coming, so we tried to put as a platform features that has an implication in networks, user context management, and other stuff actually, that wherever the computation happens, whatever the algorithms and the protocol computation happens, so that being eased out as a part of the platform enablement actually. Now coming back to the same way, if I see take the analogy forward, that what we are trying to put forward as a part of the 6G standardization is the usage of AI actually. Now, the usage of AI, again, it's an application space, but when we are trying to put in a standard, we need to understand that standard governs the way the application packet has to move on actually across the different layers. Okay, so now that is the boundary of the standard. Now, within that standard, it will never dictate that what is the method that you are trying to use for actually, what is the technology you're trying to use for. Whether you want to use what type of CNN or DNN or transfer learning, that they will never talk about. What they will talk about is that implication of the technology on the different aspect of the communication layers, and they will stop at that point itself. So there the innovation starts, saying that wherever the gaps that standard deliberately leave out actually, so there where the technology component starts getting into the algorithm development start into. Now, the same model when we are trying to put AI or the blockchain into account, into the flow of the 6G technology, same way it will happen, because the blockchain's main concern area, the main 6G's concern area, whether blockchain is trying to understand or solve it or not, that is the first impact analysis will be taking into consideration. Now, post that, the standard will stop at that point, saying that one of the application through which it is getting solved is via blockchain, and they will stop at that point, but they will not dig into that how the blockchain will be able to send the access mechanism or send the interlayer trustworthiness, a lot of things that they will leave out, because that will be taking under the next session, what we call as a security management aspect of it. So that's the way normally the standard evolves actually. So I'm not seeing there will be a push to actually put some of the concept, but how much it will be taken into consideration, it's a deliberation between the different vendors, operators, and all that stuff. So it is a long way. I'm not saying direct implication, but indirect implication, the way the NFV has put forward into the standard, the same way the blockchain also will get into.
Thank you, sir.
Probably there is a couple of questions to Dr. Debrati ma'am, and probably then we can wrap it up. Ma'am, the question goes like, in terahertz communication, will designing end devices like mobile, will it be cost effective? And then are there any drawbacks of implementing terahertz communication?
Yeah, so the first question is about the end device and the energy efficiency. That's the criteria. So going ahead, we have to design the energy efficient fashion. All the modem designs, including also the network designs, also expected to do like that. And if actually we are not capable of lowering down the cost of the end devices, how the technology will be popular. So it's always actually on our head. It should be energy efficient as well as the cost efficient. So expected to be, the end devices are like your mobile phones, expected to be low cost. But saying so, it is also dependent upon what kind of the features you are trying to improvise in it. So if you wish to have the connection, all through, space to the ground, air to the ground, to the deep sea, everywhere the device should work, or you wish it to be your medical purpose plus the communication only. So depending upon the use that you are going to have, definitely actually the different range of the devices we are expected to happen, but definitely it should be energy efficient and cost efficient also, at least for the communication as a communication device. What was the second question?
Is there any drawbacks implementing terahertz communication?
Yeah, all the challenges that I have shown in my slide, they are all, I should not say the drawback, currently they are looked into as a challenge. The biggest challenge will be to control the energy, energy efficient fashion, devising all the devices and their implementation itself. How to go ahead with that, that is expected to, the time will answer, researchers have to answer. And apart from that, I should not say something is actually any drawback in that sense. There is actually a lot of scope and lot of challenges that we have to come up with.
Yeah, thank you, ma'am. I think we are almost addressed all the questions what the participants had posted both in chat window and Q&A window. I would like to again give back the virtual podium to Dr. Aloknath Dey for closing remarks before we formally have the vote of thanks. And for all the participants, I have pasted the ComSoc Summer School link. You can go through that, and probably if you feel interested and is it on your interesting theme, you can please register yourself. So, Alok sir.
Chengappa, I have a question for Professor Mishra.
Please sir. I think Dr. Sudeep Mishra just got disconnected. No, I think he's there. Please go ahead, sir.
Yeah, please go ahead.
Oh, yeah. So, Professor Mishra, you're working on so many different topics. So just a fun question. How do your students figure out what to work on with you?
I think the common theme for us is basically, IoT and, connectivity for IoT. Right. So we are, we are working on the different aspects of it. Some of them are application oriented, but I think the common theme for all of these is, how to make this connectivity happen in the context of IoT and low power devices. So that's the theme. If you look through all of these works. So that is basically the underlying thing.
Thank you.
So thank you very much. I also had two questions which I answered in the chat. One was related to this terahertz versus VLC, and I think Professor Sen also answered that. I mean, how we are able to achieve 1 Tbps, although the range needs to be increased and all of that. So both are doing the independent work, but obviously, terahertz is kind of ahead at this point as a main driver for the 6G, but both research are ongoing. The other question was more about the density of base stations linking to terahertz and also the machine connectivity density. So those I answered, and thank you all for listening so patiently. We planned it for 3 hours. It's more than 4 hours now. Very nice to have you on Saturday morning. When we visualize this, I've been talking about B5G and having something very specifically for 6G. I'm happy that we could conceptualize and we are implementing. We had 2 hiccups in this Corona time to make the dates changed, but nonetheless, it's very fruitful today. And with IEEE Bangalore and KGP together, being able to do great things. We hope to continue this on some other topic. And definitely this is a kickstarting this 6G discussion. It's a hallmark step for us. And we should nurture this item by item in separate forums and discussions. So with that, I will hand over to Chengappa. Thank you again.
Thank you, sir, for those closing remarks. So I guess like we already had our dose of technical sessions this morning, so probably would keep it very sweet. So once again, on behalf of IEEE Bangalore ComSoc Chapter and all the office bearers, Execom members, and also IEEE Kharagpur Section, we profusely thank all the speakers and participants who stayed with us for the 6G workshop. So until we meet again for yet another interesting workshop, please stay safe, get vaccinated, and keep on your learning journey. Thank you one and all.
Thanks, see you again.
Yeah, thank you all. See you
Thank
again.
you all.
Bye.
Bye-bye.
Bye.
Thank you very
Take
much.
care.
Thank you. Bye-bye,
Thank you,
everybody.
Naveen.
Thank you. Bye.
Bye.